All right, hello, hello. I believe we are back and we are live. I appreciate you guys joining me this evening or this afternoon, rather. Today is December 7th, 2024, and we are streaming. Yeah, we're going to be finishing up chapter 3 today in data structures and algorithms. We've come a long way so far. We do have a long way to go, but this was a lot of new material that I believe was like a huge hurdle to cross in terms of, breaking through that barrier into data structures and algorithms. So we were successful in doing that. So we should be very proud, you know. But we do have a long way to go so far. I have been actually watching a lot of videos online, pardon me, just to further solidify the concepts of big O notation versus big omega versus big theta, and the respective distinctions between them. And so now we're going to be talking about some simple justification techniques. In the last stream, we we went over some just some simple algorithms and found out their time complexity, which is some examples. So now we're going to do some simple justification techniques in 3.4. Pardon me. All right. Sometimes we will want to make claims about an algorithm, such as showing that it is correct or that it runs fast. In order to rigorously make such claims, we must use mathematical language, and in order to back up such claims, we must justify or prove our statements. Fortunately, there are several simple ways to do this. Okay, so now we're going to justify our claims to the speed of an algorithm. Let's go ahead and let the Discord know that we are live. All right. Cool. By example, some claims are of the generic form. There is an element x in a set x s that has property p. To justify such a claim, we only need to produce a particular x in sequence s that has that property p, right? We can physically prove it by example. Likewise, some hard to believe claims are of the generic form, quote, every element x in a set s has property p. Likewise, some hard to believe claims, so every element has that property. To justify that such a claim is false, we will only need to produce a particular x from S that does not have the property P. So rather than, that's the instance of a counterexample. So rather than trying to prove that every instance doesn't have that or it does have that property P, maybe let's just think about it the opposite way and do that only one doesn't have the property. Ferris, thanks so much for joining and leaving a message. First one here. I appreciate you coming in. He says, nice to see you learning again. What day are you on this book? I'm not sure. I haven't been tracking the days. That would be a kind of a cool statistic, to be honest, but I haven't been tracking the days at all. And I don't really care to, I guess, because I think it's just fun to learn in general, and I don't want to put any pressure on to finish in a certain number of days. So I think we've started this book about a week ago, I think. So Jeremy Fuller, welcome. Appreciate you coming in. Good to hear from you again. Yes, back at it. We're gonna finish chapter 3 today. I'm excited to finish chapter 3. I just got myself some lunch, and so now I'm ready to get this grind going. Okay, so we have a counter example, right? Let me go to 3.4 here. Simple justification tech. Right. Okay, so we can do this by example. There is element x in set S that has property P, right? you can, right? You can display or prove by example that the element or statement is that the statement is true by showing the element and its property, it's desired, right? So by example, there's an element x in set S that has property P. So you can display or prove by example, right? Quote, by example, that the statement is true by showing the element and its desired by providing the element and its desired property. Okay, cool. So then we have a counter example, right? Which would be counterexample would be like to justify a weak of this one element that no there is. Okay, we'll make this more. We'll use the broad one so we can use the counterexample example, right? So we'll say all elements every element x in set S has property P. Element and their desired property, right? So then the counterexample would be to counter this example, just prove that one element differs. One element does not have the property in set S, right? Rather than trying to prove they all. Right, okay. We'll just leave it at that. Right, I think it's fairly straightforward. So example, so Professor Among Us. Bruh. This book is trolling us here. Professor Among Us, come on. Don't do us like that. Oh. Come on. Professor Among Us claims that every number in the form of 2 to the power of I minus 1 is a prime number. When I is an integer greater than 1, Professor Among Us is wrong. To prove Professor Among Us is wrong, we find a counterexample. Fortunately, we need not look far, for 2 to the power of 4 minus 1 is equal to 15, which is equal to 3 times 5. 15 is not a prime number. The contra attack. Contra attack. Right. Another set of justification techniques involves the use of the negative. The two primary such methods are the use of the contrapositive and the contradiction. Hey Marvin, I appreciate you coming in. Or is it Marvine? I'm sorry if I pronounced that wrong. Please forgive me, but if you could let me know how to. I appreciate it. I'm reading Data Structures and Algorithm in Python, just like in the title. We're on chapter 3 here. We're about to finish. We just learned about big O notation and some time complexity examples and some basic algorithms, and now we're just learning into just wrapping up with some like kind of justification techniques here in chapter 3. Then we'll get into some practice problems. So the two primary such methods are the use of the contrapositive and the contradiction. The use of the contrapositive method is like looking through a negative mirror. To justify if P is true, then Q is true, we establish if Q is not true, then P is not Q instead. Okay, so we have the positive, right? The contradiction, which is going to be like looking through a negative mirror. Okay, logically, the first two statements are the same, but the latter, which is called the contrapositive of the first, may be easier to think about. If P, then P is the contrapositive. No, wait. The contrapositive method is like looking through it in a negative mirror. To justify the statement if P then Q is true, we establish that if Q is not true, then P is not true instead. Logically, these two statements are the same, but the latter, which is the contrapositive of the first, may be easier to think about. Okay, got you. So this is the contrapositive. If Q is not true, then P is not true. So instead of, quote, if P is true, then Q is true, the contrapositive uses the views from the perspective of if Q is not true, then P is not true, right? Like that. Okay, cool. And then we have contrapositive. Okay, so let A be. Let's have an example here. Let A and B be integers. If A times B is even, then A is even or B is even. Okay, so let's think about this. So multiplication here, so let's do some examples. 2 times 2, well, that equals 4. 2 times 3, that equals 5. Okay, so this statement is not true, right? This statement is false. To justify this statement, right? If A or B is even, so 2 times 3, no, sorry, 2 times 3 is not 5. 2 times 3 is 6, and 2 plus 3 is 5. Sorry, we're getting warmed up here, guys. Get warmed up. So just 6. So is there anything to say? We'll do 2 times 4 is 8. 2 times 5 is 10. 2 times 6 is 12. 2 times 7 is 14. 2 times 8 is 16. Well, yes, this would be true because you're technically just by adding by 2 every time, right? Yeah, so this would be true in that case. So justify this claim, consider the contrapositive. Quote, if A is odd, then B is odd, then A times B is odd. Okay, so 3 times 3 is 9, which is odd. Okay, suppose A is equal to 2 times j plus 1, and B is equal to 2 times k plus 1 for some integers, j and k, then A times B equals... This got into it really annoying here. All right. If A is odd, B is odd, then A times B. Suppose that 2 times j plus 1 and B goes 2 times k plus 1 for some integers j and k, then A times B equals just those two functions put together. Okay, which is reduced down to this, hence AB is odd. Besides showing the use of the contrapositive justification technique, the previous example also contains an application of De Morgan's law. This helps us deal with negations, for it states that the negation of a statement of the form P or Q is quote, not P and not Q. Likewise, it states that the negation of a statement of the form P and Q is not P or not Q. Okay, this is okay, let's keep going here. Contradiction. So another negative justification technique is the justification by contradiction, which also often involves using De Morgan's law. In applying the justification by contradiction technique, we establish that a statement Q is false by first supposing that Q is false and showing that this assumption leads to a contradiction, such that 2 does not equal 2 or 1 is greater than 3. By reaching such a contradiction, we show that no consistent situation exists with Q being false, so Q must then be true. Of course, in order to reach this conclusion, we must be sure our situation is consistent before we assume Q is false. Okay, so this one basically says that if we have a statement and we want to try to prove that statement is true, well, let's contradict the statement and try to prove that it's false first. If we can then not prove it's false in any circumstance that we can think of in situations that are consistent, then the statement must be true by default. Now, is that a super great way of doing things? Maybe for the short term, but in the long term, for many inputs, probably not. But we'll see here. So we'll say, quote, if Q is true, right? We have statement says Q is true, right? To prove this statement, let's take the opposite angle and try to prove that Q is not true, right? If we can't find any situation which would prove this contradiction as true, we can assume our original statement is true. Q is true, right? Is valid. Right, so if you have a statement, Q is true, to prove this, a way to try to prove this statement would be to try to take the opposite approach or angle and prove that Q is not true. If we cannot find any justification or situation where this statement would be true, where Q is not true, then um, we can infer or assume that the original statement is valid, such being that Q is true. Marvin says, "Oh, you're getting into software engineering field." Not exactly, really. I have a degree. Back in 2021, I graduated college with a degree in Bachelor of Science of Human Biology, and I have a minor in chemistry. Um, I work as a formulation chemist right now in the professional field. I've been doing that since I graduated, and it's been fun. And just trying to learn new skills, take on new challenges, and what sparked this whole thing really quick was that I tried to. I have a lot of chemical calculations that I have to do by hand, and have some kind of intuitive calculations, um, just by with practice and with knowledge of the scope of things I'm working with, and I would and hope to and enjoy to have a computer be able to do these things for me, and so that sparked the interest in wanting to learn how to program and learn a new skill. And so I started taking CS50P through Harvard. I completed that course. I started back at the end of May, beginning of June of 2024. I completed that course at the end of the summer. I did it very part time, on and off, over the summer, as I do work full time and was taking vacations during the summer and things along those lines. And then in September, I completed, or at the end of August, beginning of September, I completed the course for my final project, and that really sparked when I completed the final project oh, I can actually do stuff with this. I can actually create stuff. I can actually make things. It really just depends upon and is limited by my own creativity and my own willingness to learn more. So I created, this channel as a way to further document that progress and maybe help others that might be wanting or are in a similar situation, or maybe just want to, hang out and have camaraderie or um, network together in terms of learning and building an environment of. I know the information can be um, is out there, very available to a lot of people, and there's a lot of information out there. But I found that there wasn't a lot of information from the beginner's point of view. Not that the beginner should be teaching information. That's not the point of this, but it might be helpful as if you were learning with someone, as if we were like in college together, in class together. Although this is just in an independent setting, we are peers, one to one, learning this together. Um, and so it might take the pressure off of things, having like a superior, like with pressure, like in a job setting or in a school setting, having it just be a peer one-on-one desire, such as just friends coming together to learn, um, could make it a lot, like more impactful on a personal level, and just make the material, I think, stick, because it takes like the stress aspect out of it, hopefully. So if that's something you're interested in, sorry about that ramble, but follow along. And yeah, so cool. So we have this example here. So let a and b be integers. If a times b is odd, then a is odd and b is odd. So we have this statement here. Let's find the example. So if a is odd, so let's do 3, and b is odd, let's do 5. Then then a times b is odd. So um, we have 15. So all the factors of 15 are 3 and 5, 1 and 15. Yeah, that would not work. Let's try like 25. That's 5 and 5, 25 and 1. What about 24? You have 6 and 4. But would you? So yeah, I don't know. Oh no, if AB is odd, right? So actually, not we couldn't start. We have to start with an odd number. So let's do like 20, um, 35. Well, if you do a 5, it obviously would not be the case, because you have to have a 5 in there to get to a 5 in the ones place. Yeah, I think that would the statement holds up. So justification. Let A be and A and B odd. We wish to show that A is odd and B is odd. So with the hope of leading to a contradiction, let's assume that opposite, namely suppose A is even and B is even. In fact, without loss of generality, we can assume that A is even since the case for B is symmetric. Let A equal 2 times J for some integer J, hence A times B equals 2J times B, okay? Which equals 2 times 2JB. That is AB is even. But this is a contradiction. A times B cannot simultaneously be odd and even. Therefore, A is odd and B is odd. Interesting. Induction and loop invariants. Most of the claims we make about a running time or a space bound involve an integer parameter n, usually denoting an intuitive notion of the size of the problem. Moreover, most of these claims are equivalent to saying some statement q times n is true for all of the n values that are greater than or equal to 1, right? This is the same statement as saying, we have some input value n that could be of some varying size as 1 or 1,000 or 1,000,000, and we have some function q that takes in the value of n, and n has to be greater than or equal to 1, right? And we have some claims evaluating this. Since this is making a claim about an infinite set of numbers, we cannot justify this exhaustively in a direct fashion, right? This is saying n can be greater. This is infinity all the way greater than 1. So I think it's taking this with a grain of salt. So induction. Okay. We can often justify claims such as those above as true. However, by using the technique of induction, this technique amounts to showing that any particular n greater than or equal to 1, there is a finite sequence of implications that starts with something known to be true and ultimately leading to show that q of n is true. Okay. Specifically, we begin a justification by induction by showing that q of n is true for n equals 1, okay, and possibly some other values n equals 2, 3, up to some value integer k for some constant k. So what it's saying is it's kind of like proving by example, but just showing these up to some point and then kind of assuming. So then we justify that the inductive step is true for n is greater than or k, namely if we show for some up to some constant k. Then we justify that the inductive quote-unquote step is true for n is greater than k, namely we show if q of k is true for all j is less than n, then q of n is true. Okay, this is getting kind of jargony, guys. I'm not going to lie. Stay with me here. We'll try to sort this out. Let's take this paragraph. Let's copy it. Go here. Explain this in more simple terms. Induction is a method used to prove that something is true for all whole numbers for values starting from a specific point. Here's a simpler way to understand it. Start small. First, we show that a statement, let's call it q of n, is true for the first number, like n equals 1, okay? Sometimes we might need to check a few starting numbers like 2, 3, all the way up to some k, okay? Build a bridge. Then we show that if the statement is true for a number n minus 1 or any smaller numbers, it must also be true for n. This is called in the inductive step, chain reaction. If both of these above steps work, then we've proven that the statement is true for all of n, starting from where we began. Okay, I get you. So that made it a lot easier. So what we're saying is we are first going to prove that we have a couple of steps, right? So induction, you have step 1, right? You want to first prove that some, so we have a function here. We want to the function f of n is true for all n values greater than or equal to 1, right? So that's our first step. So that's our problem here. We have, that's our statement. Oh my gosh, come on, stay up here. So the function f of n is true for all. So we would first, step 1, prove that that small values of n are true for f of n. Example would be n equals 1, 2, 3, ... all the way up to some integer k, right? Step 2. Second, prove that large values, quote, we'll make this in quote, large values are with respect to n are true for f of n, right? So then for this one we could say example the example would be n minus 1 so go back, that's right, n equals like that. Is it greater than 1? Okay. So then example n minus 1, n minus 2, minus 3, ... to some integer, I. Right? Some integer n minus I, sorry. Okay. So this we first prove the smallest end of the range, then we want to prove the largest end of the range with respect to n, obviously, right? Because if n is a small number, like 5, 4 is technically not a large number, but it is large with respect to the range of n, right? 1, 2, 3, 4, 5. Well, 1 is small compared to 4 with respect to n. If 5 is our largest value. So in our array or in our set or something. So thinking of it like that. Oops, bug, got it. Nope. Oh, I missed it. So then we also need to show that all the values are n minus 1. It must also be true for n. It must also be true for n itself. This is the inductive step, right? So then and n. So let's actually do n equals n, n minus 1, n minus 2, n minus 3, all the way up until n minus some integer value I, right? Or I'll do k prime and then k double prime to make it easier, kind of simpler, because I want these to be kind of similar in theory, but not the same. Like these are different in these steps, right? Okay, that's what that means. So then we'll do step 3 for induction would be the chain reaction. If both of these steps work, then we've proven that the statement is true for all n starting from where we began. So this would say, like, if both step 1 and step 2 are proven true, then the overall statement can be assumed true or valid. If both of these steps work, then we've proven that the statement is true for all n, starting from where we began. Okay, no. So it's not really is valid. The whole statement's not valid. It's we've proven that the statement is true. I'll copy this. Quote. I'll quote this from the book. Right, like that. Okay, so if both step 1 and 2 are proven true, then, quote, then we've proven that the statement is true for all n starting from where we began. Induction. Okay, awesome. That made that a lot easier to understand. The almighty or helps break things down a lot better. Okay, so let's get an example here. Prop 320. Consider the Fibonacci function big F of n, which is defined such that big F of 1 is equal to 1, big F of 2 is equal to 2, and big F of n is equal to f of n minus 2 plus f of n minus 1 for an n input of greater than 2. Okay, so if you provide f of 1, you get 1 back. If you provide f of 2, you get 2 back. But for any value greater than 2, you do this Fibonacci sequence, which just you return a value, which is the sum, right? Exactly. A Fibonacci sequence, if you remember, a Fibonacci sequence is just the next number is the sum of the two previous numbers in like for a normal Fibonacci sequence step. So you would it just says you take n minus 2, which is the second previous number, and then or 2 back from it, and then you add that to the number that's directly behind the current n value, right? And so then you just set that equal to, that's the Fibonacci for 3 would be, right? Or the third Fibonacci step, and you know, it would, yeah, which is, okay, cool. So we will show that our claim is correct by induction. So we are going to first prove the some small integer values are true, such as 1, 2, 3, all the way up to some value of k prime, or k, you know, in this first on a local viewpoint. So the base cases are n is less than or equal to 2. Okay, so it looks like we're picking 0, 1, and 2. I'm not sure if they're going to include 0 here, but we'll see. So base case is less than equal to 2. So f of 1 is equal to 1, which is less than 2. So that is true. Right? And f of 2 is equal to 2, which is less than 4. Oh, hold on, we missed a claim here. So we claim that the function of n is less than 2 to the power of n. Apologies, that was a critical part that we missed in this proposition. So we have this proposition, and the claim states that this Fibonacci sequence that's returned, right, for any value of n, the Fibonacci of that value is less than 2 to the power of that value provided. So we, for values 1, for these edge cases, these smallest edge cases in our first step of induction, we are going to put in 1. So our function, when we're given 1, we just get a value of 1 back. Well, 2 to the power of 1 is equal to 2, so 1 is less than 2. That's proven true. Okay, for now the value of 2, we look at our function here that about plugging in a value of 2 provides us a value of 2, a constant value. So we are just given a 2 back in constant time, it looks like here, and with an O in constant time, right? O of 1, and and 2 to the power of 1 is and 2 to the power of 2 is 4, which is less than 2. So that is true as well. Or 4 is greater than 2, which is true. So now we're going to do steps greater than, some numbers greater than 2. The induction step. Suppose that our claim is true for all n prime greater than n, right? So now we're doing that, we're proving numbers greater than our first one. Oh no, so for all n primes that are less than n. So consider the function f of n. Since n is less than, or n is greater than 2, right, in this induction step, for n is greater than 2. Okay, so that's our induction step here. So that's where it comes from, is this n limitation, right? So that's we have the base cases for when n is like no constant, and then we have these if cases that happen for any value that happens above those base cases, okay? So our induction step is that conditional, so n is greater than 2. We're going to claim that values, okay, so consider f of n, since n is greater than 2, consider the function f of n minus 2 plus f of function f n of minus 1. So this is that Fibonacci. Moreover, since both n minus 2 and n minus 1 are less than n, we can apply this inductive assumption, sometimes called the inductive hypothesis, to imply that f of n is less than 2 to the power of n minus 2 plus 2 to the power of n minus 1, since, okay, so what they did was we have our, initial implication up here, where our proposition, which basically states that the Fibonacci function f of n, when we take in these two values here, or n values, when we do this math for any value greater than 2, and we claim that this is our claim. So then we can say that we can insert that our claim so they take the 2 so this function is n. Trying to understand this part. We will show our claim is correct by induction. Okay. since both n minus 2 and n minus 1 are less than n, okay, yes, we can apply the inductive assumption to imply that 2 to the power of n minus 2 plus 2 to the power of n minus 1 is greater than f of n, since is less 2 to the power of n minus. This is interesting. I'm going to take this. Ooh. The almighty orb here. We're trying to prove that for the Fibonacci sequence f of n, the value of f of n is always smaller than 2 to the power of n. We will use the induction to do this. Base cases. When n equals 1, f of n equals 1, right? When n equals 2, f of 2 equals 2. Since these claims were true for these starting cases, we've completed the base step. Induction step. We assume that the claim f of k is less than 2 to the power of k is true for all values k is less than n. This assumption is called the inductive hypothesis. So we have this value here. I'm trying to see where we're trying to make the connection here. Okay, using the Fibonacci definition. Okay, let's move on. Prop 321, which is the same as proposition 3.3. So this is the summation formula for values all up to n. They'll justify this by this equality by induction. N equals 1 is the base case. Trivial for 1 equals n times n plus 1 divided by 2 if n equals 1. The induction step is if n is greater than or equal to 2. Assume that the claim is true for n prime is less than n. Consider n. So this is equal to okay. I'm gonna move past these. These are just confusing, I feel like, for no reason. I mean, they're probably important. I know they're probably important, but for the sake of what we're doing, I think like if we need these, we'll come back, but there's no sense in getting like frustrated and trying to work through those when, in all honesty, I don't even think that they're that interesting, but we'll find out. Okay, loop variants. Okay, we're almost done. Last page of the chapter, guys. I'm so done with this chapter. Loop invariants. The final justification technique we will discuss in this section is the loop invariant. To prove some statement about a loop is correct, define L in terms of a series of smaller statements. Okay, to prove that some statement L about a loop is correct, define L in terms of a series of smaller statements. L naught, L1, all the way to LK, where the initial claim L naught is true before the loop begins. If L of j minus 1 is true before iteration j, then j will be true after iteration j. The final statement, LK, implies the desired statement, L, to be true. Let us give an example, a simple example of using a loop invariant adjustment argument to justify the correctness of an algorithm. In particular, we'll use a loop invariant to justify that the function find finds the smallest index at which the element val occurs in sequence S. So we have a function here. which takes in a sequence and a value that we're trying to find inside the sequence. So we take in n, which is just going to be our length of our sequence, so the amount of data that we're iterating through. And we have j equals 0, which is our starting point, or our counter, rather. So while j is less than n, so we're going to count all the way up into the number of values in our sequence. If the sequence at that index position j, starting at 0, is equal to value, we're going to return that value. We're going to return the index that it's in, else we're going to increment j up 1, and else we'll return -1. So if return j, so then increase and then return -1, which is outside of the while loop. If it's not found, what's the return -1 statement doing here? Algorithm for finding the first index of which an element occurs in a Python list. What does the return -1 do here? I can't figure that out. What does the return? The return -1 at the end of the function serves as the default return value. The function fails to find a desired element in the list est. Here's a detailed explanation. Okay, so it just is a default, so there's no actual purpose to it. Okay, it's not an index, which is kind of misleading because -1 could be taken as the index, like the last one, right? So I don't think they should return -1 here. You return none or something. All right. Let's keep moving. Almost there. Last paragraph of the chapter, guys. Last paragraph of the chapter. Last section here. Or last two paragraphs, sorry. To show that the find is correct, we inductively define a series of statements of loop of Lj that lead to the correctness of our algorithm. Specifically, we claim that the following is true at the beginning of the iteration j of the while loop. So the loop at iteration j for some value is not equal to any of the first elements j in the elements of first j elements of S. This claim is true at the beginning of the first iteration of the loop because j is 0 and there are no elements among the first 0 in S. This is kind of trivial. True claim is said to hold vicariously. Okay, so what this is saying, right, we have some claim here, right, to show this true, that we're going to try to prove this true claim. Sorry. Oh my god. That was a bad stutter. I'm so bad. We're trying to prove that the statement is true, right, I think. It's true at the beginning of the loop because j is 0 and we have nothing else to compare. Wait, no, because you have some value given, so you're comparing j at index 0, s of index 0. Because j is 0 and there are no elements among the first 0 in the sequence. No, I'm not sure, but wouldn't we have an element at position index 0? So you have a length would be 5, right? So j is 0. Sequences are 0 index, so you would have a value at j0. So I'm not sure what this means. In iteration j, we compare element value to the element at the sequence at position index j, right? And return the index j if the two elements are equivalent, which is clearly correct and computes the algorithm in this case. If the two elements val and the sequence at that index value j are not equal, then we have found one element not equal to j. We found one more element not equal to value, and we increment the index j, right, by 1. Okay, simple. Thus, the claim, the loop of j will be true for this new value of j, hence it is true at the beginning of the next iteration. If the while loop terminates without ever returning an index in S, then we have j equals n. That is, ln is true. There are no equal elements s equal to value. Therefore, the algorithm correctly returns -1 to indicate that value is not in S. Okay, this just basically explains the while loop, but what does this really prove? Like, the initial claim is true before the loop begins. It's true at the beginning of the iteration of the for loop because j is 0, and there are no elements among the first 0 in S. But S would be 0 index, so there would be an element at that point. Which is interesting. So I'm going to take this. I don't care. I'm going to take the whole dang page. The explanation describes the loop invariant method, which is a way to verify the correctness of an algorithm by reasoning about its behavior during each iteration of a loop. Here's a breakdown of what's happening. What is a loop invariant? A loop invariant is a condition or statement. Let's take this. A condition or statement that remains true at specific points in a loop's execution. To prove an algorithm's point works correctly using a loop invariant. I'm going to copy this over here, like so. So we have the initial condition, L0, show the invariant is true before the loop begins. Maintenance, show that if the invariant is true before the iteration starts, and it remains true after the iteration. And termination, show when the loop ends, the invariant implies the algorithm's correctness. How the loop invariant works in find. The algorithm in find is supposed to locate the first occurrence of value, val, in a sequence, S. If val is not found, it returns -1. Here's how the loop invariant helps perform its correctness. Invariant definition of the loop at some position j, right? At the start of each iteration j, the variant Lj is val is not equal to any of the first elements of S. Before the loop begins, j equals 0. Since there are no elements in the first 0 elements of S, L is vacuously true. I'm going to take this. I'm going to say if S is 0 indexed, would there would be a compare happening for val at j equals 0. Yes, if S is 0 indexed as Python lists are, the first comparison happens for S0 when the loop starts. However, this does not contradict the initial condition of L0 because the invariant L0 is evaluated before the first iteration of the loop, not during it. Let me clarify. What happens before the loop? Before the loop begins, j is equal to 0. The invariant states L0 states value val is not equal to any of the first 0 elements of S. Value is not equal to any elements This is vacuously true because there are no elements in the quote first 0 elements to compare val against. What happens during the first iteration when the loop starts? The condition j is less than n is checked for the first iteration j equals 0, so the condition holds if S is non-empty. the algorithm compares s at index 0 to value. If s at index 0 is equal to value, the function immediately returns 0. If not, j is incremented. The first comparison happens during the iteration. The initial condition L0 is about the state before the loop starts, where there are no elements to compare. The first actual comparison, S0 is equal to value, happens when the loop begins. The distinction between before the loop and during the first iteration ensures the correctness of the loop invariant reasoning. Okay. Interesting. Okay. Arc 2005, thanks so much for coming in and leaving a comment. I appreciate you coming in. He says, I'm taking a DSA 1 course next semester. It's in C++. I took a C course and found it pretty hard. You guys got any tips? Oh boy. I'm learning myself, my friend. It's a grind out here. I am just trying my best to read through this book. I highly suggest, if you're going to take the course next semester, to maybe follow along with what I'm reading here. It seems that I'm learning that as well right now, and doing it self-taught using a bunch of online resources and using the stream. So yeah, thanks so much for leaving a comment though. Joseph, like they said, is Python easy? I'm not sure if it's easy because I don't really have anything to compare it to. I've never programmed in anything really else besides just HTML and CSS a little bit, but those I don't really count that much. In terms of picked up on, I thought it was fairly difficult to pick up on from a raw beginner standpoint, just because programming as a whole, I feel like, is a difficult concept to pick up on. So I don't know. I think programming is hard. I don't think Python necessarily is hard. If that makes any sense. I don't know. Yeah. Um, no, I'm not in college. I graduated in 2021. I have a Bachelor of Science in Human Biology and a minor in Chemistry. And I work as a formulation chemist right now. Thanks for the sub, Arc. I appreciate you coming in. I stream almost every day. I try to. I'm on a streak right now. I'm going to keep the streak going for as long as possible. We are growing really rapidly on the channel, which is fantastic. And I am going to start. I post videos, but I've just been busy doing these streams after work. But I'm going to try to make some videos this weekend in between the streams I do, just in regards to the Python crash course, try it yourself problem. So if you're a beginner Python learner, I myself am a beginner Python learner. I'm trying to currently transition into the intermediate area by taking on, data structures and algorithms, by also eventually taking on the Fluent Python book, right? We'll read this big old thick boy, and then we will, and then we're gonna take on the. Sorry, I get my library out every stream. I'll take on the Python machine learning book, and we actually have a couple people in the chat and that are subscribed to the channel, and in the Discord, the community Discord linked below, which is just a collection of all the resources I use, PDFs, videos, links. I just put it all in one area for the stream for everybody to use, but. We'll eventually get to these harder books after data structures and algorithms. Maybe we'll start them, simultaneously, but I don't want to get too many projects going at once. But I've already read the part 1, which is the fundamentals of Python crash course. The first 2/3 of the book, and then the back third is just practice a project and stuff, and how to kind of get a project started and things like that. I kind of just went my own route after that and started making projects on my own. But I'm going back through and uploading videos, solutions to the try it yourself practice problems, as well as, just creating some videos in general on the subject matter. So, yeah. That sounds very interesting to you. Feel free to follow along. I'm super excited to get this. Keep going here. The channel has been growing quite rapidly over the course of the last couple of weeks. We are up to over 260 subscribers, which is great. We might even cross 300 after this stream, hopefully, which would be phenomenal. So I appreciate you guys. Let's get caught up on the chat. In my opinion, Python is way easier than C. Oh, nice. Um, Ark says I took an intro to CS course in C and it destroyed me. Let me guess, you spoke assembly and that's not low enough. Structure pointers super hard to master. I'm a beginner as well. How are you enjoying your self-learning journey so far? For me, I struggle with consistency sometimes with the attempt to self-learn stuff. I'm gonna be honest. It is a struggle to get on here and learn and push myself. It's a Saturday. I'd much rather just be watching The Office right now, eating some food, hanging out, walking my dog, doing something different. But you have to think that when you sit down and study, you are also bettering yourself. And it's really a mindset you need to change rather than cup half empty, thinking of learning as a chore. Think of it as a privilege. It can be, it's a valuable thing that we are given, and I think we are take advantage of. People don't realize that you have a, a genie in your pocket now. You literally have a walking or just a living genie that can answer any question you have, and you can use it responsibly, obviously, to learn any material that we currently have information about, which is just insane. So, um, yeah, it's really limited to your own creativity and your mindset thinking, where you view learning on and teaching yourself things as more of a chore when it should be a pleasure, because you're building on yourself and you're working on yourself. You're creating new skills for yourself. It's kind of like going to the gym. That's why people like going to the gym, because they're improving themselves. Ark says, "Were you on the pre-med route in college?" Yeah, actually, that is true. When I first went to college, I started off in accounting, so in a business major. My first 2 years or a year and a half ish, um, I started off in going down into accounting. I was really good at accounting in high school. I like tutored people in the accounting courses, and you know, and so I have a fairly good understanding of business and stocks and things like that, and economics. I know quite a bit about. I currently, I dabble and have quite a passion outside of the stream in stocks in the stock market and economics. I have a portfolio, and I do a lot of day trading and trading as well. I have quite a busy schedule, but yeah, it's very that interests me as well, and so I would hopefully would eventually like to actually implement programming scripts for trading algorithms and things like that. So that's what all of this is for, you guys. Like, trust me, you want to be here. We are getting this is just the seed that is sprouting, but once we have all this information behind us and we have these tools in our belt and we're fluent in them. The key is we are fluent. We don't want to just breeze by them. Okay, we're done. We know them. No, we want to understand them solid and full, so that when we get to the situations where we need to utilize them for developing, trading bots, algorithms, for developing serum matrices, for chemical matrices that I have in mind. I have a lot of projects in mind for developing, I think like AI biomedical detection would be really cool for detecting like flaws in DNA sequences, and analyzing large DNA sequences really fast would be really interesting, or all that kind of stuff. So it's our oyster really, and so hopefully with my science background in biomedical and chemistry, um, we can, and then getting into programming, we can put this all together. So yeah. But and then sorry, besides that tangent, and then going into my sophomore, junior year ish, I was like, I cannot do this anymore. I don't like crunching other people's numbers. I just don't think I can do this anymore. So I started getting into chemistry, and I really liked chemistry. But I did not really want to go down the avenue of like principal chemistry and physical chemistry and um, like all those really in-depth like synthesizations and things like that. That stuff didn't really interest me too much, and I was just kind of exploring in college. To be honest, if I can go back, I would 100% say I think I would do computer science if I could go back in time and tell myself to pick another major. But that's all in hindsight. Um, I enjoyed it. I enjoyed chemistry. I taught the undergraduate labs when I was a senior in college. I For the freshmen and sophomores in the in the not physical but the general chemistry courses. I did the I was an undergraduate teaching fellow for chemistry courses for a couple professors, and it was paid through the university that way. So I was quite involved. But I did go with the biology route just because it kind of tied over. And again, I did not want to go down those more advanced, super advanced chemistry courses, as this wasn't super big passion. Um, Sammy says, "Howdy, everyone! Glad to be back." Awesome, Samuel. Appreciate you here. Welcome. Appreciate you coming in. Let's get the party started here. Jeremy says, "I'm taking machine learning for trading next semester. I'll let you know how it goes." Well, Jeremy, yeah, you'll have to hope maybe share some material with me so I can I'll take it on the side. I would really be interested in that actually. That'd be cool. Samuel Malero says, for DNA sequences, as you mentioned, it would be cool in the future to look into quantum computing. Interesting. Yeah, I have to, again, like we're just planting the seed here. So once we start diving into avenues, putting hours in, I think we can learn whatever we want, really. So it's okay, brother. Not many doctors are here. They are out there. They're taking a break or saving lives. I think it's great that you're still learning. College is not the end point of your learning and improving your journey. Exactly. I think a lot of people feel that after college, it's like, okay, I've finished now. Like, it's over. I don't want to take in any more information, but it really should just be the beginning. And a lot of people come out of college with a lot of ego because they were at the top of that food chain, in the education system. Um, but once you get into the professional field, you're kind of knocked down like quite rapidly. And so then after about, a year and a half, 2 years, I think people, like myself included, start to realize, oh, I got to keep learning. I got to keep doing things. I got to keep developing new skills. It's not just college isn't just the answer anymore, unfortunately, as for it was in the past, I think. Samuel says, I had finals the past week. That's why I was gone, but finally done. Well, congratulations. Let's relax. Let's chill. Let's just take all the pressure off, do some fun learning here. It's no pressure here. We're not going to do any exams, none of that. None of that. Okay. Okay, so basically, with this question that I asked earlier, I was saying like I wasn't really understanding what this was. So, the final justification technique we discussed in this section is the loop invariant. To prove some statement L about a loop is correct, define the loop in terms of its series of smaller statements where the initial claim. Okay, um, so we go through this loop. Interesting. All right, let's kind of move on here and look at that, guys. Woo! We are on to the practice problems here. So finally, oh my gosh, let's give ourselves a round of applause. Let's give ourselves a breather. We are finally here doing practice problems, and we're done with the reading for now. So we can grind through these. These might take us maybe. Oh boy, looks like we got 34 practice problems here. This might take us a little bit, but it's all right. Okay, reinforcement. All right, so let's check the chat here. Um, Hey, Alex White, I appreciate you coming in and joining the chat and leaving a message. Thanks for joining. Yeah, we've been live for a little over an hour and 13, hour 14, 15 minutes now. The more practice, the better. Yes, I feel like I feel like for the stream's sake, the practice problems are a lot more enjoyable, and I got a lot more interaction during the practice problems than during the reading. So the reading, it's just tough because it's so much jargon. I have to kind of explain things again in simple terms, but it is necessary though for setting things up for success. Okay, so um, also, guys, I did push, like, I got a request last stream to push and repo my notes and my practice problems here to my GitHub. So go ahead, and it is live, so you guys can access it yourselves watching the stream, and get access personally and see those practice problems and those solutions I have on the previous ones if you are doing chapter 1. Now I will say the chapter 1 and 2 I didn't take too many notes on because it is a lot of Python review, and I did do the Python crash course part 1 live on stream and the CS50P, so I already had a fair, really solid, kind of not really solid but solid-ish understanding of the Python basics at that point, and so I just went ahead and read the chapter and did the practice problems. And but chapter 3 is where we introduced all new material. Literally everything was new, and so that's why it took us a couple days to get through. And because I wanted to really understand it, I got through the chapter, but still I'm trying to understand it. But we'll get there, guys. So yeah, so go to the repo online on my GitHub, and the link is in the description, and you can have it for yourself, and I'll keep updating it as I go along. All right, so let's get this problem copied over. Um, 2n squared, 3n squared, 2n to the power of n. Okay. I don't like how it wraps weird sometimes. Sorry, guys. Okay, here we go. Graph the function 8n, 4n log n, 2n to the power of 2, n to the power of 3, and 2 to the power of n using a logarithmic scale for the x and y values. That is, if the function value f of n is y, plot this as a point of x and y, x coordinate at log n and y coordinate at log y. Okay, so what we'll do is let's go ahead and pull up Desmos. Let's open up the graphing calculator, and so we want to plot f of n, right? And I'll just copy this down. Ooh. A few times. So is equal to, we have 8n here. We have is equal to 4n log n. We have is equal to 2n to the power of 2. We have is equal to n to the power of 3. And then we have is equal to 2 to the power of n. Right. So let's zoom in on the graph here. But we need to make this log base 2 here. Here we go. So this is our graph. Perfect, right there. All right. So what's going on here exactly? So it just wanted us to graph them. That was the whole point of the problem, really. Okay, so we graphed them. Now let's see. Let's interpret these, right? So we know that this is a linear function. This just takes in some constant 8, which we don't count. So in our time complexity for the upper bound would be big O of n time for this red function here. And as we increase proportionally here for every value of n, we get 8 back, or 8x back. So if we go up to x equals 1, we should get 8, I believe. So, right there, x equals 1, and we get 8, right? Perfect. So that's what that means, is basically for every value of n in our data set, it is skewed by multiple of 8, thus creating a higher, steeper slope than typically what we've seen, okay? So now we have this blue function here, which is 4n log n. We know that the n log n function is is faster than the is a little bit slower than the linear function. Doesn't have us use just a basic a log function. Interesting. All right. Oh, whoops. I hate when it does this. Come on. Okay. So this blue function will tell us. Actually, I'm going to take this problem. I'm going to leave it. I'm going to copy this text. I'm going to give it to the almighty orb. And I want it to graph it for me here. And I want to analyze, because I want it to do the logarithmic scales. Okay, let's update this. Okay. Let's see what it can do here, boys. Get caught up in the chat while we give this a sec. Samuel says, this is beautiful. Awesome. I'm glad you're enjoying it. Appreciate you. All right. Varun says, you the code. Wow, I'm getting a lot of love today, guys. Thank you so much. I appreciate you guys. Alex, thanks for looking out for that typo. Yeah, we corrected that one. Okay, here's the graph of the functions as plotted in logarithmic scales for both the x and y axes. Okay, so as you can see, that exponential function just completely has that growth rate of just through the moon. But on a scale, so just give me the Python code for it. Give me more x values. The orb graph makes much more sense. Okay, whatever. So I'm gonna try. Can I just zoom in here? Come on. No. Whatever. Copy image. Let's go into VS Code. This guy. Can I just paste this image in here? Will it let me paste? No. I'm gonna add the file. I'm gonna add it in here. I will, so this is going to be what? R. Come on, let me type, please. I'll save it, R 3.1. Is it 3.1 image. Okay, and then I will go put this inside of the folder here so we can use it. Where'd it go? Date modified. Oh, there it is. Okay, there we go. So now we have this in our VS Code. Cool. All right. Yes, Alex White, this is time complexity analysis. So chapter 3 was we introduced the 7 functions of that we're going to be using in the book, right? So let me go ahead and show you. So chapter 3, let's go ahead and for those that are new here, let's do a quick overview of chapter 3 before we dive into these problems. So chapter 3, we're introduced to data structures, which are a systematic way of organizing and accessing data. We didn't exactly dive into these too heavily, but we just kind of defined them. We were then introduced to an algorithm, which is just a step-by-step way to execute, executing code for an input or values or a thing like that along those lines. In a certain amount of time is the key thing. So these algorithms have running time, which is the natural measure of quote unquote goodness. A computer solutions should run as fast as possible, right? So this is just the measure of how quote unquote good an algorithm is based on its running time or its speed it can execute values. More specifically, values that are very large or inputs that are very large, such as arrays that have many different inputs or like upwards of millions and millions of inputs and things along those lines, or data points. So we also define what an epoch is. They give a really kind of bad definition in my terms, but this was just like a benchmark time for starting an algorithm. Was in referring to actually timing an algorithm within a script or within a program, is if you had a loop or some sort of lines of code that you wanted to track at what point that during the running time of the entire project you would establish an epoch or whatever to at this point is where we want to take a quote like a timestamp for tracking our algorithm's time within the overall time of the project from my understanding of it. Now we also define what primitive operations were. Now primitive operations, I kind of struggled with understanding them at first because this book honestly uses a lot of jargon and I think it could be broken down a lot more simple if you had someone else write it, unfortunately. But it does have a lot of good information, so we're not going to just quit and we're going to power through. So what these primitive operations are the most like basic actions a computer can perform during a program's execution. So right, just any sort of math operations, plus, addition, multiplication, doing comparisons, is less than, equals to, is this number that, is it equal, data access, right? If we have a list and we're just accessing a single point in that list, like an integer or a index value, just not looping through, right, but just accessing a single point, then that's a primitive operation. We have control flow, so just general loop in general, without these are excluding the inclusion of outside data sources, right, which is crucial. So then we have like function calls in themselves, that don't take in data inputs and things like that. So yeah, or I mean they might be able to in certain circumstances, but obviously I think primitive operations are supposed to be things that are in O of 1 time or constant time. So we have a ceiling, right, and a floor. I should probably add a floor definition here and add that in. But so the ceiling basically is just rounds up to the nearest whole number, and the floor rounds down to the nearest whole number. So if you're in between and a float, you would always round up for a ceiling function, and a floor function would always just forcibly round that number down. So then that kind of got past the definition section, and we dove into the actual reading portion, which is we start with 3.1, which is experimental studies, and this was just talked about kind of those epochs, God, and primitive operations again, and counting them. So we um, can use the time module and the time function and the clock function to measure those sections of our code and create those timestamps. Oh, this part of the code ran in this amount of time. But these aren't perfect because the time function um, is impacted by other processes going on in the background of the computer. So, if you're have things going on that are slowing down the programs or processing data in the background, maybe the person's like rendering a video in the back. I don't know. It's affected by other processes going on that could affect the runtimes. The clock, rather, this one measures the physical count of the CPU cycles, but obviously this would have limitations due to the physical hardware capacities and limitations of the CPU for individual users. So we have to take that into account for this one. So we can also use the time it module, which can automate time evaluations with repetitions to account for variance among trials. Um, Now, I believe that this just like populates a bunch of different reps, um, rather than a single time stamp for, okay, this took 10 seconds. Rather, it generates multiple occurrences of these evaluations through repetitions and kind of bakes into this variance and gives you kind of a range of speeds, right? Um, all right, we have a couple comments. Uh, Alex White says, oh no, so Dan H. Hey Dan, I appreciate you coming in and leaving a message. He says, how often do you go back and revise those notes do you take? Um, Honestly, I don't really know. I'll just go if I go back and look through them and something updates, I'll revise them. But I often go back and reference things that I've written quite often for definitions or for code or for further understanding. But I'm also using this as a tool for you guys as well, to A, follow along with what I'm saying on a physical level, and then B, to reference it when I'm offline and use it in your own studies as well. Alex White says, that's actually pretty cool. Benchmarking is dope. Certain operations take more time than others. Whenever I see a for loop or while loop, I just know the time complexity is going to increase, especially OS interactions that happen all the time. You can't really help it. Awesome. Thank you for your comments. I appreciate you joining in. All right. So yeah, we can then count these primitive operations, right? I believe this has something to do with these time it modules, but I'm not exactly sure. But this just basically says that for some function that we have that takes in input, we run over these primitive operations, a number of we can count these up in terms of t, right? For our runtime. These primitive operations in total take up, variable t, which is equivalent to the runtime. And so it's characterized the number of primitive operations that are performed as a function on the input size n, um, which is just as simple as counting up the number of operations in the function and the algorithm itself, right? Um, the worst case scenario, right, the slowest observed runtimes of the algorithm used as a base level for improvement. So now we're going to start getting into functions and like into big O notation and things like that. So um, we always consider in this book the worst case scenario for optimizing an algorithm, because then we can account for having all focus on greater minimizing the total number of operations needed. So just by planning for the worst case, you're covered in most aspects rather than only trying to achieve the best. You might be limited and have some gaps in your programs or things like that from my interpretation. So we were then introduced to the 7 algorithm or functions used in this book, and the first one is the constant time function, where f of n, some function that takes in a input value of n, returns just some individual constant value every single time. So if you think of this as a graph, right, Desmos. Think of this as a graph, just some value, constant value c of 5, right? No matter, as our input size increases from 2 to 6 to 10 to 14 to 18, our our output value always remains 5. It does not change no matter what. So this is really good for handling large amounts of data, because no matter what, we have a constant time. We know exactly the amount of time or the amount of energy or amount of, whatever it is that would be needed to make this happen, and it would just be 5 or whatever, unit that would account for in the circumstance. Now we have logarithm functions after that, which, in a sense, if you think of, we need to understand what a logarithm is. Logarithms have a base value, which just says the reduction, kind of means like the value that we're going to reduce or the step value almost. Think of logarithm as like steps. You're manipulating some value a number of times until you get to something, and that in theory, if you think about that, that's just the same thing as an exponent. So that's what you're solving for logarithms. So if you in computer science, we always when we give a logarithm, we always are inferred that it's log base 2, because of binary and how computers work, and unless otherwise specified, calculators have log base 10 by their default. So we're going to have a log base 2, and for some integer value n, right? So all this statement right here means, right, log base 2n is 2 is going to be our base, n is going to be our exponent value, and to equal is going to be, well, what would, hold on. So yeah, example. See, even I get logs mixed up sometimes too. So if we have log base 3 of n is equal to 27, it's just 3 to the power of n is equal to 27. So and then we can solve for n in that case, to figure out what that would be. And so how is this actually working under the hood is that the base value is the steps that are occurring as we're dividing by each time, which gives us our exponent value. So in the case of a log base 2, we are halving our n value every single time and counting those number of halves. And as we sum up those halves, that is our exponent value. So for example, if we have a value of 2, we can, or a 4, we have 4, if n is 4, right, with the log base 2, we have 4, that is 1/2, we have it once, now we have a new value of 2. We have that, we divide that by 2 and we get down to 1, so we can divide that by 2 and get down to a floor value of 1 2 whole times. So the value of, our exponent value is 2, which makes sense. Log base 2 of 4 for value of 4 is equal to 2, because 2 to the power of 2 is 4, which is our value of n. If that makes any sense. I'm sorry if I'm not the best at explaining logarithms. I'm sure that there are other resources out there that are more math focused, but just know that the log base 2 is just your large value, your whatever yours inside the log itself is what is being raised itself as the exponent, and then the equals is what you are is the actual number of steps that the logarithm provided. So this provided 27 steps. Right. So if this is log base 2 for n, we say 4, or let's say 8, right? This would be 2 to the power of n is equal to 8. So what do we have to raise 2 to get to 8? Well, we have to raise 2 to 3 to get to 8, right? 2 times 2 is 4, times 2 is 8. Right, 2. how many times can we divide n by 2? 2 would be 3. Let's get rid of that. I don't think that was correct. Right? N is equal to 3 in this case. 2 to the power of 3. 2 times 2 is 4 times 2 is 8. Hey Lucas, thanks for joining. I appreciate you coming in and leaving a comment here. Thanks for joining the channel. How are you doing today? Okay, so then we learned about linear functions, right? So these are also in order from most efficient to least efficient in terms of their or slowest growth rate to fastest growth rate. So we can view that as efficiency. So as you know, constant functions are completely flat, so they have no growth rate, whereas linear log functions have a slight growth rate over time as they approach infinity, large numbers. Linear functions, are one-to-one. For every n value you provide, you get n back. So for n is 1, you get 1. N is 2, you get 2. N is 3, you get 3, creating that linear line straight through one-to-one to the graph. We learned about n log n functions. So we have log n above, but this just for every time we, for the function assigns an input n value to the n times the log n, the log base n, right? So this just skews the logarithm function by a factor of n every time. Now, the next one is quadratic. We often see this one for nested for loops. The next one after that is cubic, which functions which we see with maybe triple nested for loops, but it's often can be misleading because I've seen some people have a triple nested for loop, but that third for loop just is a conditional only for linear time, and so they might already assume by seeing 3 nested for loops that, oh, that's a cubic time function, or O of n cubed complexity, and they just didn't read the problem closely enough, or the function itself. So then we have an exponential function after that, which just takes some base value and raises it to the power of our input. And as you can probably tell, if you have a large input, raising it to the power of for a large input as the power is going to just provide you an insanely large answer. So this one is extremely slow and inefficient. All right, let's continue moving on here, you guys. Let me check something real quick. All right, guys, we crossed 275 subs. We are at 276. Hurrah, hurrah. Thank you so much. I appreciate you guys showing some love and spending time with me here, learning. We're all growing together as programmers and learning new things. So I'm so excited that the channel's growing. It's really exciting. Thank you so much. All right, so we then got into asymptotic analysis. So this might, if you remember from, pre-calculus, maybe even into algebra 2, definitely into calculus, you saw a lot of asymptotes. And what asymptotes were certain values that as we approached infinity, or as we approached these values, we could not cross them, and we just kind of stalled out, or they're just barriers that our functions could not cross, or they have a difficulty approaching, we'll say, for lack of better words. So we were introduced to some new analysis for computing the complexity times and describing the timings of functions. So we are given big O notation, which is where we say we have some function g f of n, right? Then we have some function g, which also takes in the input n, multiplied by some constant c, right? Now, this is pretty cryptic to look at just off the initial what's going on here. But if you actually take two functions that have time complexities that are similar, that are the same, and plug them into these values and then actually solve for a constant value c, you will come to find out that these will become true if both of those statements are in big O notation. So if you want to put this to the test, you can actually create dummy functions and plug in values, and for n, meeting these conditions for n not, and trying them. So, but big O notation, from my understanding, and obviously take this with a grain of salt. I'm still learning this. I'm learning myself. I'm trying to apply these concepts and take them in. But from what I understand, it is like in the definition, is the upper bound, or the worst case scenario, that the function slash the algorithm can perform. Right, so it describes the upper bound or the worst case time complexity scenario that the algorithm can slash will perform at. Um, so, right, because if we go back to that graph from our previous example here, start our functions at the top in orange going down to blue, so from most efficient to um, least efficient. Now we are missing one function here, the log function, but we do have just an n log n, which just skews the log function by a certain factor of n, slightly increasing our values. But as you can see down here for small inputs, it is pretty negligible. Now the exponential function is really efficient, as you can see, um, way down here. I'll zoom way in. This blue line has a slight gap. It performs more efficient than all these other functions because it has a lower y value, or lower running time, if that's what we're depicting y value is in terms of this time, for larger x values or n values, input values. But as we get to a certain point, when the data starts to really increase here on a logarithmic scale, as you can see by these numbers, we start to really branch out and start to separate from the pack. Can I zoom out? How do I, is it just minus? And alt? I don't want to keep, there we go. Should hold. Cool. So as we start to gain, because timing complexity, right, we are caring about large input values. So as we start to increase these input values for 10 to the 1, 10 to the 2, 10 to the 3, these graphs will start to separate and to become more distinct. And we could definitely see, if I were to ask GBD to show me some more graph here. But it's pretty explained here by this exponential function that it cannot handle large amounts of data because it starts to really rapidly increase with a extreme growth rate. So for data for 10 to the 2, for an input value of 10 to the 2, this function would give back a 10 to the 30 input, whereas these other ones, if we could optimize this algorithm in some way to have an O of n upper bound more similar to a linear or a logarithmic, or a maybe even a quadratic in some circumstances, it would be better suited for these for these input ranges in this range. Now, exactly how that's determined, well, we'll get into that. Now, I'm going to say this with a grain of salt, is big omega and big theta I am not that great at. um, I still am struggling with trying to understand these ones. I don't really understand how they really differ from big O notation. I know that they do. I know that big theta obviously differs quite heavily, but I definitely am trying to understand big omega better. So explain big omega time complexity in simple terms. I understand big O, but I'm having trouble differentiating between the two. Big omega time complexity is a way of describing the best case scenario of an algorithm, just like big O is used to describe the worst case scenario. Okay, so describes the lower bound or the quote best case scenario, best case time complexity scenario that the algorithm can / will perform at, right? Okay. Here's a simple breakdown. Big O tells you how the algorithm's running time grows at most as the input size increases. It's a way of describing the upper bound or worst case performance. For example, an algorithm, whoops, for example, if an algorithm has O of n time complexity, it means that in the worst case, its running time will grow linearly with its input size. Okay. Big omega tells you how the algorithm's running time grows at least as its input size, as the input size increases. It describes the lower bound or best case performance. So if an algorithm has omega of n time, it means that the best case running time will grow at least linear to its input size. So if a function, so what I'm having a problem then, so example, consider a linear search algorithm that looks for a specific item in an unsorted list. Worst case, big O. If the item is not in the list or it's at the very end, the algorithm will check every item. This gives O of n time complexity, where n is the number of items in the list. So the best case scenario for an algorithm for big omega, if the item in the first one in the list, the algorithm will find it immediately just taking one step. This gives omega of 1 time complexity since it only takes constant time at its best case. Oh my god. Okay, I get it now. Okay, so this is what it essentially means is this is algorithm dependent, right? I'm going to preface this here. Algorithm dependent, right? Meaning that you have to think about the different case scenarios that the algorithm will encounter when it is ran, right? So I'm going to come down here and add an example here and say you have an algorithm that runs where you are trying to find a value in an unsorted list, right? So you have some function f of n. you have an algorithm f of n where you're trying to some value in an unsorted list n, right? The worst case scenario right? The worst case scenario for this algorithm would be that the worst case scenario that the algorithm would encounter would be that the desired is at the end of the list, meaning every value preceding had to be evaluated. This has a time complexity of big O of n time, right? So then the best case scenario for this specific example, for this specific algorithm, the best case scenario would be the best case scenario that the algorithm f of n would encounter would be that the desired value is at the start of the list, right? So if the value is at the start of the list for this specific algorithm, the best case scenario would be that it is detected right off the bat. So the best case scenario, the start of the list, meaning that only the first value was evaluated and returned, right? This has a time complexity of O of 1 time, or constant time, right? So I wasn't thinking about this in a specific algorithm by algorithm basis. I was trying to determine like, oh well, if it's worst case scenario, if it's according to this graph, I was thinking about this. Oh well, if it's the worst case scenario is exponential, where then, but I was thinking, well, if that's the lower bound, then the upper bound would be just the next one over. Well, no, the upper bound would be, it's dependent upon how the algorithm runs. It's not going to be just this pink line or the cubic function, right? That's not going to be the upper bound because the algorithm somehow falls into here. There might be a scenario where the algorithm actually has a runtime which is way down here because it has this odd edge case where it actually detected the value somewhat soon and didn't have to go through a bunch of values and end up way up here. Like, what if it detected it way sooner and was down here and has this best case more closely resembling to something else? So that is that definitely helps with that. Okay, hopefully that helps you guys as well. Let me know if I'm on the right track. If you disagree, this is definitely open for interpretation as I am learning this as well, and I want to be able to know that I'm getting the right information and at least conveying the right information to you guys as well. So if you disagree or have something else, then please let me know. I will um, definitely take that into account. Hey Vansh, thanks so much for joining. I appreciate you coming back, and it's good to hear from you again. How are you doing? How's your weekend going? So okay. So you need to evaluate big O and omega on an individual algorithm or function basis, each accounting for various edge cases that the algorithm might encounter during a runtime. Yes, exactly. When analyzing the time complexity of big O and big omega, you evaluate each algorithm or function on a case-by-case basis, considering how it behaves under different conditions or inputs. You also need to account for various edge cases that might influence its performance. Here's how you can approach it. The big O worst case, yeah. So, um, in the case of detecting a value in an unsorted list, how would we then identify the big theta with a O of n time and a big omega of 1 time. In the case of detecting a value in an unsorted list using a linear search algorithm, big theta represents the tight bound on the running time. This means it gives the time complexity for the algorithm in both the best and worst cases, combining the two. If we already know that big O time complexity is O of n in the worst case when the value is at the end or not present, right? If I had to search through every value in the list and found it at the end of the list or just didn't find it at all, the big omega time complexity is omega of 1 in the best case where the value is in the first element, right? If the value is at the very start of the list and it didn't have to iterate past any more integer values than 1 or the index value of 0, in that case, the same thing vice versa, it would have just a constant time of omega, right? Whereas big theta, then the big theta time complexity would be O of n because the algorithm will always need to search through the list at least once, regardless of where the value is located. Here is why. Big O describes the worst case scenario. The algorithm might need to check every element in the list, so the worst time complexity is O of n. Big omega describes the best case scenario. If the value is the first element, the algorithm will find it in constant time, so the best case is omega of 1. However, big theta is the time complexity that bounds the algorithm in both the best and worst cases simultaneously. Since the algorithm is performing a linear scan, and in most situations, apart from the best case, it will visit each element at least once, the tight bound that describes the algorithm's performance is in general is a big theta of n. This means that on average, the algorithm will take linear time n steps to detect a value, that there's no better or worse case that significantly changes this behavior in a way that would result in a different growth rate. Interesting. So so you just evaluate the two then, and the big theta is just the one that is big theta then the most likely scenario. Big theta is not necessarily the most likely scenario, but it rather represents a tight bound for the algorithm's time complexity, meaning it reflects the overall performance of the algorithm in both the best and worst cases, as well as how it behaves on average. think about it. Here's how you think about it. Big theta describes the exact or tight bound, meaning it covers both the best case and worst cases, giving a complete picture of the algorithm's behavior across all inputs. Give me, so if I had a function like, if we had n log n plus, let's just do like, let's do like 2n log n plus log n plus 2n, right? So if we have this function, what would this be? So we know that we have, walk me through determining the big O, omega, and theta. Let's walk through the big O for this function. Simplify the function. So we'll simplify it. First, simplify the function by identifying the dominant terms. Here's the original function. Okay, the term 2n log n grows faster than 2n or log n as n increases because it combines with linear and logarithmic component, right? So yes, we know that based on our definitions, the log function, the log is going to be faster than the linear, which is going to be faster than the n log n, right? Yes. The term 2n is linear, and the term n log n grows much slower than both 2n log n and 2n. Got you? So the term 2n log n dominates the others, right? We know that this term dominates the other two because this one is the slowest or the bottlenecking term. For large n's that become insignificant in comparison. We can therefore ignore the smaller terms log n and 2n when analyzing the overall growth rate of the function. So we can focus on the dominant term, f of n is equal to 2n log n. So step 2, worst case scenario. Big O describes the upper bound of the function or the worst case scenario for the function's growth rate. It tells us the maximum rate at which the function can grow as n increases, right? So the term 2n log n dominates, therefore the growth rate of the function is asymptotically O of n log n. Thus, the big O time complexity is O of function n is O of n log n. The big omega, best case. The big omega describes the lower bound of the function or the best case scenario of the function's growth rate. It tells us the minimum rate at which a function's growth occurs as n increases. For f of n, 2n log n plus 2n, given even the best case, the 2n log n term always grows faster than the n log 2n or log n because n log grows slower, right? Therefore, the big omega time complexity is, right, big omega n log n. So because we had this term dominating and it is significantly slower than all these other ones, it is taking precedent over big O and big omega. But for big theta, let's look here for tight bound. The big theta represents the exact growth rate of the function combining both the worst and best case. If an algorithm is big theta g of n, it means the function grows at the same rate as g of n, both in the best and worst cases for large n input values. For this function, since it dominates and grows at the same rate, and the worst, right, it dominates and grows at the same rate in both the best and worst cases, the big theta complexity of the big O and big omega complexities is big theta n log n. Interesting. Cool. That definitely helped. So, I know that might have seemed like a lot or kind of like a ramble or deep dive into it, but I wanted to get an actual example, and that definitely helped to show. So, big theta. So the let me go back to this to where I said. of n. Okay. Okay. Cool. So we've been streaming 2 hours and 10 minutes, guys. I appreciate you coming in with me today. We are going to be streaming for the next little while, or at least until I get tired here. So I'm feeling good for right now. And we finished chapter 3, and I was just going through and doing a refresher on what we covered. I felt like it was good to go over that before we dive actually into the problems here. But all right, so cool. So we finished 3-1. 3-1 is just this answer here. So I'm actually that takes care of that problem. So let's go ahead and do R 3.2 key dot pi. Ooh. All right, cool. Let's get a check on the. Let's get a check over here on the channel. See how we're doing. Awesome, we're at 279. That's so cool, guys. All right. 3.2. The number of operations executed by algorithms A and B is n log n. Okay, hold on. Let's focus here. Sorry, guys. Let's focus. Focus. All right, let's copy this, paste it in to here. The number of operations executed by algorithms A and B is 8n log n and 2n squared respectively. Determine n naught such that A is better than B for n is greater than or equal to n naught. The number of operations executed by algorithms A and B is 8n log n and 2n squared respectively. Determine n naught such that A is better than B. Okay, so let's try. I think what we can do here is go to our graphs. We need to graph these. 8n log n. F of n is equal to, and f of n is equal to 2n squared. Okay. So we need to do a log base 2 here, like that. Okay, so we need to determine at what point the number of operations executed by an algorithm. Determine n naught such that A is better. So A is this function red. So at what point is A is better than B for an n value greater than or equal to n naught? Oh, so we're looking at the wrong problem. Sorry. 8n, 2n squared, respectively. Determine n naught. So we want to determine the first number in the sequence, or the first number in the sequence that would make A better than B for all values of n that are greater than or equal to the first value. So according to my function here, right, this is our inflection point between these two graphs. So wouldn't the anybody have any input on what this is exactly asking? So the number of operations executed by A and B is A in log n and respectively. Determine n0 such that A is better than B for all values greater. So A is only better than B for values less than 1. Or less than this value here. But B has a way better running time, for sure, after this inflection point. Don't answer this, but help me understand the question. I plotted the functions on a graph, and where they inflect would be where they would be the n value determining the crossing point of efficiency. To determine the value of n naught such that the algorithm A is better than algorithm B for n values greater than n or equal to n naught, we needed to find the number of operations n becomes less than the number of operations of B. Given algorithm A has a time complexity of that, and algorithm B has a time complexity of 2n squared, we need to solve for n naught where 8n log n is less than 2n log squared. Simplify the inequalities. So it set them to divide both sides equally. Now we need to solve the inequality for n log n is less than n. To do this, analytically we can approximate or use numerical methods because solving the inequality algebraically is difficult. We can use the values of n to find n naught, the smallest value inequality holds. To find the exact crossing point where for n log n is equal to n, we can estimate the value numerically using a graph. Greater than or equal to 16, A will perform. What? Why wouldn't it give us... So what happens at y equals 16? You get 2 points. X equals 2. What about for x equals 2? Right, if we have an x equals 2, 8, 16. So actually, if we have x equals 1, right, this function doesn't even produce data, whereas this function does. So b is technically better than a at x equals 1, right? Now at x equals 2, function b produces a value of 8, whereas function a produces a value of 16. Right? So, which Desmos is like scaling was better. Is there a way to like auto scale? So the smallest value of n naught such that the algorithm A becomes better than algorithm B for is approximately n naught equals 16. For all values for n greater than or equal to 16, algorithm A will outperform B. So I put 16 here. When I plot these two functions on a graph, they inflect at why is this not the point at which function A becomes more or function oh I'm dumb. I'm so dumb. Oh my gosh, you guys, I'm so dumb. Okay, so all this is saying was, look, hear me out. So I get it. So we were doing it right. We were doing it completely right. As I wasn't reading this correctly. So A is better than B. Function A is our red function. We need to know at what point function A crosses back over to the right of function B. Because if function A is, because right now, function B processes data here in the positive, whereas function A cannot. It is less than. It comes up to this point and inflects at 1. At this point here, function A is processing small amounts of data and returning values. So we inflect, and boom, if we go to x is equal to 16, we will see that these will cross back over eventually and inflect once again right here. Boom. Why is this? How can I make this a different color? Whatever. Right, we are inflecting once again right here, and function A is becoming more efficient at x equals 16. So to determine this mathematically, what they did was they the inflection point refers to two functions complexities intersect across the graph. Time complexity starts to outperform, right? To find these Algorithm A has a time complexity of 8n log n. Algorithm B has a time complexity of 2n squared. We need to solve for n naught where 8n log n is less than 2n squared. Right? We want to solve for when at the very point, right, where this inflection happens is what we're solving for. Where this algorithm is less than this, and yeah, exactly. And so simplify the inequality. So 8n log n squared, 8n log n is less than or equal to n log n squared. We can divide both sides of the equality by 2n, assuming that n is greater than 0. So this gives us 4 log n is less than n. So now we can solve this inequality mathematically by plugging in values for n. So if we try n equals 10, which will give us about 4, and n equals 10. So 4 is less than 10, so this holds. For n equals 100, this gives us a value of 8, which is less than 100, so this holds. And then for 12, for n of 1,000 gives us a value of 12, and that holds. So as you can see, as n increases, the inequality holds more clearly, and it becomes evident that for such large n values, 4n log n will always be true. Yes. Now we estimate the crossing point numerically. To find the exact crossing point where 4 log n equals n, we can estimate the value numerically using a graph tool or solver. Okay, yeah, so then it's B. Eight n log n. Oh, so we'll say A is equal to, quote, 8n log n, right? B is equal to, quote, 2 to the power, 2n to the power of 2, right? So we'll say these two, you can solve this problem by graphing both time complexities as a function function is equal to f of n. The inflection as n increases, the inflection point between these graphs determine where the or quote crossing over between these graphs determine the n value where they becomes less. Perfect. So you can solve this problem by graphing both time complexities as functions equal to f of n. And then as n increases, the x axis. The inflection point or crossing over between these graphs determine the n value where the b function of time becomes less efficient than that of a. So then we'll say these graphs cross or inflect at x equals 16, at n equals 16. Meaning that the minimum number of operations needed to be executed in order for algo A to become more efficient than algo B. Perfect. Hey Wasil, I appreciate you joining and leaving a comment on this Saturday. Thanks so much for spending some time with me here. We're just solving some reinforcement problems here at the end of chapter 3. This problem we were asked to determine, we have function A and B, these two algorithms. The function A has a time complexity of 8n log n, whereas function B has a time complexity of 2n squared. And we were trying to determine the point, respectively, at which n naught, right, such that the first point within our, our data set, that A becomes more efficient than B for all values greater than or equal to n naught, right? So what we did was we graphed these two time complexities, and we found that they crossed over in the positive x or n direction at x equals 16. So at this point, the A graph, or the red graph, right? If I zoom way in here, right, zoom, right, they get way closer and closer until they cross way up here in this kind of general range here. Now it's kind of so small that it's kind of in this range, but it's there, yeah, right here. Cool. I appreciate you joining. Okay. That takes care of that problem. So R 3.4 key dot pi. Okay. Oh, sorry, 3.3. I mean, let's do R 3.3. Okay. Let's take 3.3. Okay. The number of operations executed by algorithms A and B is 40n squared and 2n cubed, right? Respectively. Determine n naught, the first position of n, such that A is better than B for all values of n greater than that first position. So this is the same kind of problem as we did before, right? So what we can do is, I can also say, I can try it the other way around, like where, right, we want to know where 40n squared is less than 2n cubed, right? Now, can we reduce this down anymore? My exponent rules, oh, I fucking suck at exponent rules. If we divide out by 2n squared, that'll take that down to, right, if we, can we reduce down by a factor of 2n squared on both sides? Can we reduce that down? So this will become just 2n. This will become n to the power of 1, or just n divided by 20, and this will be, so this will become 20, which is less than 2, which is less than n. I don't know if I'm doing this reduction right for my exponent rules. So if I'm not, please let me know. But I'm sure we'll find out in a second. So this becomes 20n, or 20 is less than n. So n has to be 20. Now let's graph it. Let's see if we're right. Or n has to be 21 in order to make this statement true. So let's see here. We got 40n squared. And we've got 2n cubed. Okay, let's go down here. Okay, we got our functions. Okay, our blue function b is definitely more efficient as it processes more data, right? It has a slower growth rate than this one for more integers. Let me say x is equal to 21. Let's see what happens here. No, okay. Make this way bigger. We gotta scroll way out. How do you adjust the scale on these guys? Okay, well the graph makes it hard, so let's put this here. Or let's go back, sorry, here. Oh no, here. Okay. When n equals 20. Okay, so it's greater than or equal to 20. Oh, it's at what point does the statement become not true? At n equals 20, right? This statement becomes not true at n equals 20 because it's not greater than or equal to. If n equal or 19, that would be 20 is less than n, which is not true. Right, yeah, n equals 20. At n equals 20, function or algo A becomes more efficient than algo B. Hey, General Talks, I appreciate you coming in and leaving a comment today. Thanks so much for joining me, and how are you doing today? Cool. So that's the answer to that problem, right? So awesome. That one felt a lot better than the one before it. Okay, 3-4. Give an example of a function that is plotted the same on a log-log scale, that is, it is on a standard scale. Okay, give an example of a function that is plotted the same on a log-to-log scale as it is on a standard scale. A linear function would be plotted the same, right? Constant would be the same. Linear, constant, right? What else would be considered the same out of our functions? So would a constant function would look the same? A logarithmic function would not. It would be different. Here, linear function would look the same. N log n function, quadratic, would be skewed more. Okay, alright, so that's my answer for this one. Let's see what we got here. A function that is plotted the same on both the standard log scale and the log-log scales is a power function in the form of C, where some constant and k is a positive or negative real number. Y. On a standard scale, linear scale, function is plotted with the usual xy axes. On a log-to-log scale, both the xy axes are logarithmic. For a function f of x equals to c times x value of k, if we take the logarithm of both sides, we get log c plus k times log x. The equation represents a straight line on a log-log scale with a slope of k and y-intercept of log c. Example 2. Example. On a standard plot, it will look like a parabola. On a log-to-log plot, it will be a straight line with a slope of 2. In this case, the shape, the line, is preserved on the scales, so the function is plotted the same way. What would a linear function and a constant function would not be plotted the same on a log-to-log scale as they are on a standard scale. Linear functions on a standard scale, a linear function is represented as a straight line with a slope m and an intercept b. On a log-to-log scale, the transformation would involve taking the logarithm of both sides' x and y values. This would not result in a straight line unless the function is in the form of power law, and it does not preserve the linearity when plotted on a log-to-log scale. For a linear function, cooked, right? Got cooked there. Got that wrong. Okay, so why exactly? So the answer is a quadratic function. So exponential are the only ones. Actually, exponential functions do not behave the same on a standard scale and log scale. Let's break this down. Then what the hell is this? Power functions? So it's power functions. Yes. Are the ones that are plotted the same on both standard and log-to-log scale. On a standard line, a power function appears as a curve parabolic if k is positive or decaying if k is negative. On a log scale, both the x and y axes are logarithmic. When you take the logarithm of both sides of the equation, f of x, log f of x is equal to log times c, which is log c plus log of x, plus k times log of x. This results in a straight line with a slope k, y-intercept. The plot is linear. Ah, okay, I see. This is your mx plus b. It transforms it into a linear function. Interesting. But it's plotted the same? The result is a straight line with a slope. The plot is linear, but the relationship between the values and the axes is preserved. Would this not have a curve on the standard scale and a straight line on the log scale? Yes, you're absolutely right. I apologize for the confusion earlier. Let me clarify the distinction. Power functions following happens on a standard scale, linear scale. Power function generally appears as a curve. If k is greater than 0, the curve will grow towards upwards, convex. If k is 1, it'll appear as a straight line to the original linear function. On a log scale, both axes are logarithmic, meaning we plot log x on both x and log f of x on y-axis. So let me go back to my Desmos here. What happens if I plot f of x is equal to c times x to the power of c times x to the power of k. So this just gives us a straight line. Okay. And then if you do log f of x is equal to the log of c plus k times log x. Ooh, didn't like that. Did not like that one bit. Right, what? F of x just log f of x. So then, what I don't get is these don't look the same. The heck? Come on. So for constant values, interesting. Okay, so what this says is this guy here. F of x is equal to c times x to the power of k, right? So these would not be the same line on a graph. Here's the same about standard unless here's a breakdown. So then what would answer this question? The answer to the question, what type of function we plot, is actually a constant function. Yeah, no I said that like 20 minutes ago. Oh my gosh, this thing just led me down like a huge rabbit hole for no reason. It's constant function. Right? If I take f of x is equal to c, I set c to 1.5 and I log at this, f of x, and that'll provide you a different value on a different, no. See, it doesn't give you 1.5, give you, shoot, so then what if I did 2 to the power of x, make this x is equal to like 5 log 5. That doesn't give the same graph. We get a linear line when we log it though. Now what if we were to log both sides of this function? c is different than log than c. I correct for the confusion. When a constant function is plotted on a log scale, it does not look the same on a standard scale. It appears as a horizontal line, y equals c on a log to log scale. The equation becomes log c versus a constant horizontal line. This is not the same. To correct the answer, the only type of function that look the same on both the standard scale and a log scale is a linear function in the form f of x is equal to x. Y on a standard scale, f of x is a straight line with a slope of 1. Its transforms becomes log x. The result is a straight line, slope of 1. This wouldn't provide I don't think if k is equal to 1, so f of x, x to the power of k is equal to 1. This one doesn't make any sense. This one's interesting. I'm gonna have to look up some more resources on this one. Let's move on to R35. Get some actual practice here. Can we stop with this explain BS? Like, it's kind of annoying. Explain why the plot of the function n to the power of c is a straight line with a slope c on a log to log scale. Explain why the plot. Oh, so it is exponent functions. The f of n to the power of c. Explain why the plot with a slope c on a log scale curve. Explain why the plot of the function n times c, n to the power of c, is a straight line with slope c on a scale log to log curve. So you would do f of n is equal to n to the power of c, right? This would go to log f of n is equal to the log of n to the power of c. So this gets reduced down to that, right? What's my logarithm rule? Oops. For slope c on a log scale. So this reflects right, so then this would essentially resemble, right, a y equals m times x, just like that. Take the log of both sides don't want to use it. I'm gonna use cool. This is our linear equation. It's the right, so this question is saying, like, what we've been kind of, we already had this answer kind of revealed to us in our previous questions, right? So this one talked about, well, what example would be similar, the same on a log to log scale as it is on a standard scale? Well, power functions with some power associated with it, raising our our associate n value to some power would cause it to have the same, because if we take the log of our y, which is f of n, and we take the log of our x values, which are this side of the equation, then just by we bring the c out front by logging the n, just by some logarithmic principles, this fits the form of y equals m times x, right? So this fits the linear equation, the log version of the power equation above, right? And so the c is equal to the slope, which is equal to m in this case. Or m is equal to slope, rather. Which until turns c is equal to slope. Cool, that takes care of that problem. So r3.6 underscore keyed up high. Let's try this one. Hopefully we get some more actual practice with them. Here we go. What is the sum of all even numbers of 0 to 2 times n for any positive integer n? Whoa, here we go. What is the sum of all even numbers from 2 to n for any positive number integer of n for any positive integer n, right? Well, this just has to do with that sum equation that we talked about earlier in the chapter, I believe. And what that expressed was that the values of so if we go back in the chapter a little ways, for that summation, that was taking place, where was that at? Summation. Here we go. So what is the sum of all of the even numbers from 0 to 2n, 2 times n for any positive integer of n? Well, the sum would be so summation. What is the sum of all even numbers from n sum is so we take I don't know. I don't know, guys. I'm gonna be honest. This is summations. A notation that appears again and again in analysis of a data structure algorithm is a summation, which is defined as follows. So given some integer f of 0 plus f of 0 all the way up to f of b. So if we have this case, right, up to 2 times n, it'd be get out of your bug. It'd be like I equals 0 sum to n to 2n, right, for function f of I is equal to f at 0 plus f of 0 plus 1 all the way up until f of 2n. So another way we can write this function is that where a and b are integers and a is less than or equal to b. Summations arise in data structures and algorithms analysis because the running times of loops naturally give rise to summations. Using summation, we can rewrite the formula of proposition 3.3 as follows. Where's prop 3.3? Prop 3.1, prop 3.3. Okay. For any integer of n to 0 until n. So why are we dividing by 2 though? I don't understand that. The formula of the sum of the first n natural numbers is given by this. The reason why we divide by 2 is to account for the fact that each pair of terms adds up to the same total. To further explain further, you can think of the sum of sequence of terms. You can rewrite the sum backwards as that. Now you add the two versions together, the original and the reversed, and you get this. Each pair of terms adds up to n plus 1, and they're n terms, so all the terms of our pairs are n times n plus 1. Since we add the sum twice, we need to divide by the original sum. So if you're going from 0 to 2n, though, you want to keep the duplicated sum, if that's the case, right? So it would be so let's just like take an example. I'm gonna write you some piece of paper actually. Now we're gonna write stuff down. Okay. So let's say we have an n value of 10. N equals 10. No, let's do n equals 5. Rather, n equals 5. So if we're going to add up all the values from 1, so 0 plus 1 plus 2 plus so what they did was so if s is equal to 0 plus 1 plus 2 all the way plus dot plus n, right? And then sequence also equals to n minus 1, n minus 2, dot, all the way up until 1. Dot plus 1. Now if we combine these statements together, right, you get this. Now add the two versions together. So we get 2s is equal to 2n plus 2 times n minus 1 plus no, not 2 times. Okay, so if we have a sequence, this does not make, okay, I'm trying to figure this out. I'm trying to write my notes here. So if we have a sequence S, right, and S goes from 0 plus 1 plus 2 plus dot, all the way until n, right? And then we can reverse the sequence order and go from n to n plus n minus 1 plus n minus 2 plus dot, all the way up until 1, right? Now we add these sequences together. And how does it add them together? just directly over the sequences. Okay, so then it'd be 2s is equal to 0 plus n, 1 plus n minus 1, 2 plus n minus 2, Talia B says, or sorry, Tala says, keep at it, dude. Self-taught here myself, still learning actually. Well, I appreciate you coming in and leaving some kind words. We're just currently trying to work through this problem here using this example and trying to put it into our terms. Plus 1 plus n. Okay. So if that's the case, we can distribute this guy. No, we can't. That's not the case. So we need to add in. So this just goes to 0 plus n would be n. N plus 1 plus negative 1 would just be n. 2 plus negative 2 would just be n. N dot 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 1 plus n, right? So it would be n times n plus 1. So I think the answer to this problem is just n times n plus 1 would be our solution. What is the sum of all even numbers from any positive integer n? So n times n plus 1. So let's think about this. You have an even number from 0 to 2 times n. So if we did 5 for n, that's 0 to 10. The sum of 0 to 10, 1 plus 3, 7, 6, 10, 15, 21, 28, 36, 45. Which would be 4, 5, 6 times 5, 35. Okay, so if we have, let's say, an n value of 5 or of 2, right? If n equals 2, in this case, so it'd be 0 to 4. So then, and if we plug that into our equation, the sum of 0 to 4, so 0 plus 1 would be 1, plus 2 would be 3, plus 3 would be 6, plus 4 would be 10, right? So 0 to 4 would be 10. Now, if we did 4 here, plus be 5 times 2 would be 10. So yes, I believe that is our answer. So what I did here, guys, bear with me, okay? So I think I solved this one. So our answer would be just 1 plus, or n times n plus 1, right? This would be our answer, I believe, for any positive integer n. Right, like that. So then let's go ahead and take this problem. I believe I solved this problem. Don't tell me the answer, but coach me through it if I am wrong. I believe the answer is n times n plus 1. Okay, you're on the right track. Let's break down your work and check your work. The sum of even numbers from 0 to 2n can be written as 0. Oh, the sum for all even numbers. Oh, shoot. Oh, I did not see that part. Oh my gosh. Dang it. Okay, so hold on. Let me retry this before I go on. So if we have S is equal to, or sequence is equal to, starting at 0, 0 plus 2 plus 4, dot dot plus dot dot dot, all the way up until 2 times n. And then our sequence in reverse order to find the reverse of that, and we could do n, or 2 times n, right, plus 2 times n minus 1 plus 2 times n minus 2 dot 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 all the way to 0. So now we're going to add these up. So we have 2 sequence times 2 is equal to 0 plus 2n plus 2 plus 2n minus 1 plus 4 times plus 2n minus 2 plus 2n plus 0, right? So then what I'm going to do is I'm going to reduce that down. So now we have 2n plus, the 2 gets added to the 1. So we have 2n minus, or 2n plus 1 plus the 4 gets added over to the negative 2. So that becomes 2. So it's 2n plus 2 all the way dot 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 until 2n. No, it would go to n. plus some value. Two times n plus 1. So this is difficult, I'm not gonna lie. So what they do, so they have this notation here, right? So the sequence is equal to 0 plus 2 plus 4 plus dot 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 plus all the way up to 2n, right? Notice that all these numbers are multiples of 2. Can you factor out 2 from each of them? Term, what does this term, the sum of is n? Notice that all of these numbers are multiples of 2. Can you factor out the 2 from each of them? What does that give you in terms of the sum of numbers from 0 to n? So if you factor out 2, be 2 times 0 plus 1 plus 2 plus dot 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 n. Okay, so it's just 2 times 0 plus 1 plus 2 plus dot 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 all the way to n. The sum of numbers from 2 to from 0 to 0 to n are multiplied by 2. Exactly. Now that you factored out the 2, the sum inside the parentheses is the sum of all integers of 0 to n, which you already know sum up as a sum up, right? The sum of integers from 0 to n is given by this formula that we've already discovered in the past. Now, using this information, the sum of all even numbers from 0 to 2n becomes no. We wouldn't you need to, so this would obviously reduce down that's what I thought. But no, that's not the case. The sum of all even numbers is 0 to 2n is indeed n plus 1. Correct. Great job. You were correct with your right answer. Cool. I was right. I was right the whole time. Oh my gosh. AI, what are you doing? AI is a great tool, but sometimes it can be pretty goofy. So interesting. I'm interested though because if you factor out 2 out of all of them, you're summing all the way up to which we know can be 2 times that, but it's weird though because I did it wrong the first time. I did I just kind of insinuated, right? If we are trying to find, if we're trying to find the value, we can just drop, I just kind of thought about this as just dropping the 2 right there, just removing the divide by 2, because instead of dividing by 2, we're trying to find 2n, up to 2n. If this is the sum of all values, right, which is dividing by 2 because you sum up them twice from front to back, and if we're trying to find all the values up to 2n, you can think of it as the summation from 0 to n with 2i, making each number you are summing up even. Yes, because when you multiply a number by 2, it becomes even. So you're just doubling the list, basically. Doubling the value of the list as a total. Thus, we're just removing the division by 2 here. It's as simple as that. Cool. So, I just did a different approach, really. I kind of did it the wrong approach, but I got the right answer. I initially was doing the sequence of 0 plus 1 plus 2 all the way to n. And then thinking about it, well, I just need to drop the divide by 2 because I am not going to then, I'm doubling my sequence value of 2n, and so I can keep that doubled in there. I don't need to divide it out. But the correct way of going about it and thinking about it was to go 0 plus 2 plus 4 all the way to 2n, and then reverse the sequence from there, 2n plus 2n minus 1 plus 2n minus 2 all the way down to 0. Reduce that down gives you 2n plus 2n plus 1 plus 2n plus 2 all the way up until 2n whatever plus k, for every value in the list, or 2n plus n, right? And then you would go ahead and factor out a 2 out of all that. Yeah, interesting. Okay, so we have this. Let's copy this into our problem here. Right. If you're adding from 0 to 2n, this actually becomes 2n times 2n plus 1 divided by n. Yeah, that's what I have right here. That's where I was getting a 2n here at the end. Okay, let's think about this. So for summing up all the values, the sum of even numbers from 0 to 2n can be written as, so the sequence is equal to 0 plus 2 plus 4 plus dot 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 plus 2n, all the way to 2n. That's our sequence, right? That's our sequence. Now, if we have the other sequence, in the sequence in the reverse order is equal to 2n plus 2n minus 1 plus 2n minus 2 all the way down plus dot 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 0. Right? I'm going to write this out. So then we got, so this is s is equal to this. Then we have another line here of s is also equal to 2n minus 1, 2n minus 2, or sorry, these should be pluses, plus dot 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 plus all the way down to 0, or to 2n minus n, or 2n minus 2n. Zero. It's probably easier to think about it. So then what we're going to do is we have a new sequence, right? Sequence times 2 is equal to 0 plus 2n plus 2 plus 2n minus 1 plus 4 plus 2n minus 2 plus dot 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 plus 2n plus 0, right? So we have 1, 2, 3, 4 terms, 1, 2, 3, 4 terms, and they all line up appropriately. So I'm going to space these out so these line up better, so we can see them, how they correspond, right, like so. Okay, this is forward. Okay, so then this reduces down to 2 times s is equal to oh, you're right. So this would be 2n minus 2 because this has to be, we are skipping odd numbers. Thank you so much, Legend27. I appreciate you giving me that comment. So what he said is this cannot be 2n minus 1 because this would give us an odd value, and we are only iterating through a sequence of even values. So this would have to be 2n minus 2 minus 4, right? Exactly. So that's what's going wrong. So now we have 2 here, and now we have 4 here. Right? So now we can reduce this down to just 2n plus the 2 adds to the negative 2, creating just 2n plus the 4 adds to the 4, right? This isn't being multiplied by, this is being added, so we can't do the, what that little trick from algebra way back, I forgot the name of it, I've been out of math class for so long. But we can't distribute this 4. We have to add this 4 to the like term of the negative 4. So this can be 2n again, plus dot dot dot, all the way up until, till 2n, right? Now, something's not right here again. We have something incorrect here. So why? Let's say, can you show me the reverse sum order for that. Okay. So what am I missing here? Why is this off? Like Legend 27, do you know why? So if this is my sequence in the forward order, 0 plus 2 plus 4 all the way up until 2n, right? If I sum these sequences together, I get 0 plus 2n and 0 plus 2n. Why am I getting 2n plus 0 on the right end? You're right to point out the issue. When you reverse the sum, you pair in the following way. Now let's correctly pair the terms. Legend 27 says there would be n plus terms of 2n. Now let's correctly pair the terms from those two sums. The first term of the original is 0 pairs with 2n. The second is 2 with pairs with 2n minus 2, and so on until the last pair is 2n minus with 0. So the 2s looks like this. This is what my 2s looks like. 0 plus 2n plus 2 plus 4n minus 2, 2n minus 0, right? Now we sum up. Now each pair sums to 2n, but we only go up to n pairs, not n plus 1, so you have 2n times n. Okay, ChatGPT is wrong. It's n plus 1, not n, since we are starting from 0. I'm not sure what you're referring to, my friend. So, okay, we'll stop with the GPT and we'll just work with what we have here. So if I have 0 plus 2n, 2 plus 2n minus 2, 4 plus 2n minus 4, right, all the way up until 2n, this gives me this reduced sequence. This gives me this reduced to, reduced. This gives me a reduced 2s sequence, right? So how does this go down further then? Because you can factor out a 2 out of all these. It's just 2n times n. So 2n plus 2n plus dot 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 all plus 2n all the way to factor the n 2n all the way to 2n. Factor out the 2n becomes 2n, 1 plus 1 plus... Okay, so if you factor out the 2n, right, 2 times s is equal to 2n times 1 plus 1 plus 1 plus plus dot dot dot. So how do you get n plus 1 in your parenthesis? You factored out the n out of the parenthesis, my friend. Or out of the equation. You're on the right track with the steps you've outlined. Let's break it down clearly. You want to find the sum of all the even numbers from 0 to 2n. So we have this sequence. Now let's reverse the order of the sequence. 2n all the way down to 0. Now let's add the originals. Now let's add the original sum and the reverse sum term by term. Each of these pairs up to 2n. Now there are n plus 1 terms in total, so 2 times n plus 1. Finally, divide by 2 to get the original sum. So yeah, why, if we factor out a 2 out of all of 2n out of all of these, why do I still have an n remaining inside of my parenthesis here? Now there are n plus 1 terms in total. What? That doesn't make any sense, in my opinion. I don't get how n plus 1 remains when we factored 2n out. Let's clarify how the n plus 1 term remains when we factor 2n out of the equation. We reached the equation 2n times n plus 1. Now let's break it down step by step. We paired the terms. Each pair term sums up to 2n, and there are n plus 1 such pairs because the even number... There are n plus 1 such pairs because the number of even numbers from 0 to 2n is n plus 1. From the very first s, you said it's 0 plus 2 plus 4 plus dot 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 plus 2n, right? If we divide by 2, it's going to be 0 plus 1 plus 2 plus dot 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 all the way to n. From 1 minus n, that's already n numbers. From 1 minus n, that's already n numbers. Since we have a 0, we have to add a 1. N plus 1. If we divide by 2, it's going to be 0 plus 1 plus 2 all the way to n. From 1 to n. That's already... I'm sorry if this is frustrating for you guys, but I'm just not wrapping my head around this entirely. So, no. So, step by step, we have the sum from 0 to 2n. Then we reverse the order of the sum. When we add the original sum and the reverse sum term by term, we get this, right? Which is what I have here. Now each pair sums to 2n, so we have this, right? I have that, okay? There are n plus 1 terms. Because the number of even numbers from 0 to 2n is n plus 1. There are n plus 1 terms because the number of even numbers from 0 to 2n is n plus 1. So if n is 5, the number of even numbers would be 0, 2, 4. Oh, so it's 10. So actually, so if n is 4, that's 8. So it would be 0, 2, 4, 6, 8. 0, 2, 4, 6, 8. Which is 5. Even numbers. So it'll be 4 plus 1. Okay. I get what you're saying because you have a 0. So the sum becomes 2n times n plus 1. And then we factor out the 2. Here, n plus 1 comes from the fact that there are n plus 1 terms of pairs of terms. Why the n plus 1 is still there? You have n plus 1 pairs, and each add up to 2n. The 2n is just a value that each pair sums to. The n plus 1 just comes from the number of pairs because there are summing all numbers. So n times n plus 1 factors to 2. So this will factor down to 2 times s is equal to 2n times n plus 1. Right, and then we will make this next line will be s is equal to 2n times n plus 1 divided by 2, all of this. Right? And so then this reduces down even further to s is equal to n times n plus 1. Right? And we can actually check this, right? And say, let's say that n is equal to 4. So I could probably write like a def sum even with some n value, right? We're going to do a count is equal to 0 for a counter. We're going to say return n times n plus 1, right? So if I go sum even for 8, right, and I run that. Shoot. Oh. What? What am I doing wrong? Int not callable. Sum even 8. Object not callable. There we go. So then if I do, let's do sum even for 4. So this will sum 0, 2, and 4. So this is going to be 6, right? 20. Bruh. Print. Four. 20. No, okay, so that's not right. We need to print oh, I'm sorry, it's 2n. So we need 2n. So we'll 2 times n. If it's 4, then it's 0 plus 2. So 2, 6, 12, 20, because it's 2n. Oh, whoops, sorry. Cool, yeah, so it's 2n, right? So 2n, this is right. We have it right originally here. So because we aren't dividing by 2 to solve the original, so if we were dividing this whole thing by 2, it would go something like that, and then this would give us the 10 for the original. If it was 4, it'd be 2 plus 0 plus 2 plus 4 would be 6. 5. 4 plus 1 would be 5 times 2 is 10. And then sum of all the even numbers up to 4 would be 0, 2, and 4, which would give me 6. So what's going on here? What? The n times n plus 1 divided by, that's the summation from 1 to 4, which is 10. summation of 1, 2, 4. So 1 plus 2 would be 3, plus 3 would be 6, plus 4 would be 10. So this just does the summation. Yeah, this is the, okay, yeah, you're right. So this, right, is the summation equation in general. This is the summation equation times 2 for 2n. Is this summing all even numbers, though? So if I did 4, 2n would be 8. So it'd be 2 plus 4 plus 6 plus 8, which would give me 6 plus 6 plus 8, which would give me 12 plus 8 would give me 20. Okay, yeah, so that is right. Gotcha. Legend 27 says the n times n plus 1 divided by 2, that's a summation from 1 to 4, which is 10, not limiting to even. N plus times n plus 1 is the summation from 0 to 2n when we only want even. Exactly. Muna says, what's the name of the book you're studying? Yeah, so this book that we're looking at here is called Data Structures and Algorithms in Python. You can either Google online and find the PDF if you would like to take a stab at this yourself, or I created a Discord linked below where I have just compiled all of my study resources I've been using so far into one area for my viewers and supporters to have easy access to them. It's completely free, as I would never charge for this information, as I am a beginner in it as well. There I also cover Python Crash Course, which I read live on the channel. We read this. We will eventually get to machine learning in Python, and then we will eventually hopefully get to fluent Python as well. So, but for now, I do have these resources uploaded to the Discord, but, oh my gosh, bent the book, the cover, shoot, that's annoying. Yeah, but I do have resources for Python Crash Course uploaded right then. Yeah. So, Roeth, sorry, Roeth says, n times n plus 1 didn't include 0, as 0 is neither odd or even. Gotcha. Okay, cool. So this essentially works as expected. So that's the solution to 3.6. Let's go down here. Okay, let's move on to R3.7. Okay. And let's go ahead and copy this in. Okay, show that the following two statements are equivalent. A, the running time of algorithm A is always O of f of n. Okay. In the worst case, the running time of algorithm A is O of f of n. Show that the following statements are equivalent. So A is equal to O, right? So A is equal to big O of f of n, right? The worst case running time for algorithm A is O of f of n. So really quick. Okay, so we learned that big O so then we know that if function A has big O notation, that means that function A is equal to or is less than or equal to C times G of n, right? So we know that that's the case for A. So Muna says, I want to learn data structures and algorithms in Python, but I'm also a beginner, though probably know a lot less than you. Is there any math background needed for the book? Um, I wouldn't say there's any specific math background needed, but you definitely need to know what functions are, notations of functions, understanding loops really well. Um, definitely, I definitely think you need to understand the basics of Python. For sure, loops, while loops, and for loops. Understanding how indexing works is crucial. Those are things I wouldn't have been able to do this without that. Um, but just the biggest portion of this is the function aspect. So understanding just how functions work, and what they look like, how they're manipulated in algebra, things like that is kind of essential. It seems like. Internet and spectator says, isn't big O notation always worst case? Yes, it's always worst. It's worst case scenario. So how are we going to show that these two statements are equivalent? The running time of algorithm A is always O of function n. So A is equal to O of function n, right? In the worst case scenario, the running time of algorithm A is A of O of function n. In the worst case scenario, so O of f of n is less than or equal to C times G of n, right? Just by swapping these in. Show that the following two statements are equivalent. To prove that the two statements are equivalent, we need to understand the difference between the two constants and show that they imply one another. Statement A, the running time of algorithm A is always O of f of n. This means that for all values of n, the running time of algorithm A is bounded above by some constant multiple of the function f of n. Formally, this can be expressed as, right, a of n is less than or equal to c times c, f of n for some constant c. Okay, so a of n for some constant c of f of n, right? So we were on the right track with this. So for some constant c greater than 0, right? This is saying that no matter what the running time of algorithm A grows at a rate that is asymptotically bound by the f of n. Statement B, in the worst case, the running time of algorithm A is O of f of n. This means that even in the worst case scenario, the maximum possible running times of the algorithm, oh my gosh. This means that even in the worst case scenario, the maximum possible running time of algorithm A is bounded above the constant multiple of f of n. Okay, formally, A worst is that, right? So A worst of n is less than or equal to c times f of n. So proving the equivalence, A implies B. If the running time of A is always O of f of n in statement A, this means that for all values of n, the running time is bounded by c times f of n. In particular, this holds in the worst case scenario as well. Since the worst case running time is simply a special case by the running time for some n, the worst case running time will also be bounded by c of f of n. Thus, statement A implies B. B implies A. If the running time of A is O of f of n, in the worst case statement B, it implies that the worst case scenario. So if the running time of A is O of f of n, in the worst case statement B, it means that the worst case scenario, the running time is bounded by c of f of n. Now, if we know that the worst case running time is bounded by c of f of n, we can infer that in general the running time of A will not exceed c of f of n, c times f of n, for any input size. This is because the worst case scenario is most demanding for all other cases. Will perform at or below this threshold. Therefore, since A implies B and B implies A, we can conclude the statements are indeed equivalent. So these basically just are equal to one another. Right? All right, that kind of solves that one. It's kind of more, there isn't really like a way to super say it specifically how they want it, but okay, 3-8. Order the following functions from asymptotic. Order the following functions by asymptotic growth rate. Okay. For n 2 to the power of n. And then n to the power of 2 plus 10n, 3n, 3 to the power of n cubed, and n log n. Okay. So first we have this guy. We need to order these in order of asymptotic growth rate. So we know that we have an exponential function. We have some function here with the power. Which this is just not including n, so this is just in some constant time. So this is going to be the fastest function. So number 1 is going to be 2. So this first one is going to be 2 to the power of 10 is going to be the first answer, the fastest in line 1. Next, we have an n log n with a constant 4 out front. And then we have 2 being raised to the log power of n, right? So we're logging n in this case, so it's not a crazy large exponent, which is quite interesting. Because compared to an n log n. Rather than just raising 2 to the power of n, we're raising it to log base 2n. So we are factoring it, scaling it down way, way lower, which is interesting. So I kind of want to see how these graphs actually interact, right? So let's do f of n is equal to 4n log n. Then we have f of n is equal to 2 to the power of log n. Interesting. So even though you have an exponential function, right, which is considered the worst case scenario, because we have it's not being raised to a power necessary proportional or linear to that of n, it's being raised to the power to the log of n, log base 2 of n. Specify that. That looks a lot better. More what I was thinking of. That looked a little bit too constant. So now we have a kind of a linear function almost. It is a linear function actually. Huh. Why is this linear? Yeah, the log n definitely scales this one down quite a bit, but this creates a linear function. If we log f of n, if we get rid of this, let's log f of n. See what happens. Hold up. So why exactly does this function give us a linear value when we're on a scale here? Hey Anthony Ham, I appreciate you coming in again. Thanks for joining me. He says 2 to the power of log 2 base n reduces to just n. Okay, so you mind explaining why that's the case? So 2 to the power of log base 2 n, right? So let's first figure out what log with base 2 n equals. So that means that we're finding 2 to what power equals 2 to the n power is equal to I'm just not familiar with those log rules per se. So if we have log base 2 times n in the exponent, this shows a proof to how it reduces. Number raised to a log. Looks like you're asking about a number raised to a logarithm. Typically, this looks like a to raised to log b c, where a is the base of the exponent, is the logarithm with c as the base, with c and b as base. Okay, got you. Muna says, this question isn't relevant to what you're studying, but I noticed you're using a MacBook. I'm going into college soon and would probably get a new computer. What do you recommend? Do you recommend a Mac over Windows / Linux? Now I'm not a super computer savvy person. I I have experience with both Windows and Mac. I've never really programmed on a Windows computer. I sold my Windows computer. I just kind of got out of like gaming and things like that. I kind of stopped doing that a few years back, and so I had like a powerful Windows desktop that I wasn't using, that I was using primarily before, and so I sold that and ended up getting this MacBook to end up to program and to have be more portable, so I could program on the go, and because I didn't have a desire or passion to really game anymore. But um, I what I really like about the MacBook that I think really excels it over my Windows experience. Yes, the Windows was a lot more powerful. It it had a lot more maybe features in terms of its like implementation and what you could change about it. But I the MacBook really just kind of strips all that down. Like it kind of, by allowing you to have less features to play with, it kind of more promotes you to focus on what you're actually working on. It also helps, the portability aspect obviously help, but you can get that with any laptop. Um, the the streamline ability to be able to pass files between my phone and my computer and my girlfriend's MacBook and her phone and any other user with a Mac and their iPhone is just it's like one to none. It can is it's so streamlined, so seamless, and so perfect in my opinion. Like I can set up an iCloud drive and share it with my girlfriend through text message, through our iMessage. She can be synced up that way. I can, edit a certain song for her dance or whatever that she does through some music editing. I can drop that file there, and then she has access to it no matter what. Yeah, there's things like Dropbox and stuff, but no, she doesn't have to have an app for Dropbox. All it is just iPhone. It's completely, that whole universe was really made it. And and to be frank, because of that aspect, I don't think I will ever go back, unfortunately. I really like Windows. I like the what it provided me. I used it all the way up until this computer. I even bought Intel MacBooks in the past and sold them after I bought them because I liked my Windows machine better. But ever since getting a M chip MacBook, I have the M3 MacBook Pro, the M3 Pro MacBook Pro. Um, I don't think I'll ever go back. This renders my videos faster than it did in the past. It has less glitches, like the Adobe suite in general that I use to edit videos, edit graphics, all that stuff doesn't crash on me as much as Windows. Windows has a lot more bugs when it comes to programs, um, and drivers and things like that. Um, you know, it's those are some of my reasons. I don't know if anyone else has any other reasons that they would prefer, but also just a lot of tutorials out there are on Mac for programming, which does help. It makes it a little bit easier for finding information. Um, you know, I'm struggling to think of some other ones besides obviously the huge aspects were just the portability and the being able to transfer files, data, pictures, anything through AirDrop and through iCloud Share and stuff. And it just makes it so much easier than having to use third-party applications like Dropbox, OneDrive. I mean, it's just so much less intuitive on Windows. Like, it just, I think they overcomplicate things to be technical, and just this, you don't need to be, in all honesty, like the simpler the better in my opinion. Now some other people might disagree, they want to have that control, but for the mass majority of people, I believe just keep it simple, stupid, is key. Okay, so Anthony says there's a rule that states that log base b, with n to n is equal to n times log. Okay, got you. So if we have 2 to the power of log base 2 times n, if we have 2 to the power of log base 2 to n. That's the same thing as saying, oh, sorry. Okay, I'm trying to put these variables where they go. So there's our log n. So here we go. So properties. Change the base formula. Logarithm base c can be written using the change of base formula. How can I simplify 2 to the power of log base 2 n? To simplify this expression, you can use the fundamental property of logarithms and exponents. The expression 2 to the power of log base 2 times n can be simplified directly using the following identity. A to the power of log is equal to, is just directly equal to x. Oh. Okay, so we have a log property here. Let's add in this logarithmic property into our notes. So we have logarithms. So we have or I'll come down at the bottom of this chapter and just add in logarithm properties. Logarithm slash exponential properties. So then we'll say that a to the power of log base b times x is equal to just x. So this would be here go example 2 to the power of log base 2 times n would just equal n. Got you. Okay, so let's get caught up in the chat here. The Legend 27 says, Muna, it depends on what program you're going into. If you are going into CS, then it'll be helpful to learn Linux, but obviously there will be a learning curve. Roeth says, check out number raised to log rule. Gotcha. Alex White says, at Muna, also something that is helpful is that Mac uses a Unix-based command line system, which is that Linux will use. Linux is overall just a lot more reliable to use if getting into CS. Ray313, thanks for joining. I appreciate you coming in and leaving a message and saying hello. Thank you so much. Okay, Muna says, I want to get into either math or computer science or both. Linux sounds fun to learn, but I can only get one computer and I don't know how compatible it is with things I will use. If that's the case, Muna, I honestly would just stick with a MacBook. The new M4s just came out, and so I think you should really consider looking at either getting an M2 or an M3 book. MacBook Pro, those books just went on sale because of those new ones were just launched, and the M2s and M3s, they are so similar in spec with the M4s that Apple won't even compare them when releasing the specs differences. They compare them back with the M1 chip because they're trying, I guess it's marketing. They're trying to show increased numbers, and by showing a 0.5x or a 25% increase over the M1 versus a 5% increase over the M3, they're kind of picking and choosing or cherry picking their statistics, which is kind of funny and honestly a little bit shady, but I don't know. It's Apple. They have those marketing techniques that they use. But the M2, in my opinion, will take care of all your needs. But if you're wanting for something that's a little bit more future proof, maybe do that one upgrade to the M3 Pro chip, which is obviously on sale because the M4s are now out. And so it'll be a little bit cheaper, a little bit more expensive than the M2, but maybe will last you about another year or two longer than the M2 would. So I'm planning on keeping my M3 Pro for the next, you know, 5 to 7 years before I upgrade again. So this will last me plenty a long time, and I really love this MacBook. I have the M3 Pro MacBook Pro 14 inch in the space black color. It has not the base M3 Pro chip, but the upgraded M3 Pro chip. I know it's very confusing. There's an M3, an M3 Pro, and an M3 Max, and in between those, they have base variations and upgraded variations. I have the not the M3 Pro base, but the M3 Pro upgraded, and I also allotted for the 36 gigabytes of RAM, or 36 or 38, 36, I can't remember, 36 gigabytes of RAM to handle my streaming open, my programs open, my learning open, my Safari open at the same time, my GPT open. So I wanted to be able to handle a lot of onboard random access memory for having a lot of tabs and for streaming and stuff. So that's why I opted to upgrade the memory. But for just basic purposes, that 18 that they provide will be satisfactory. I think the M4s have a minimum of the 18 now. Um, uh, Rajesh Pilla, thanks so much for coming in. I really appreciate you coming in, leaving a message. Thanks for joining the channel. Feel free to check out the description for the Discord if you're wanting to get access to the PDF for the data structures and algorithms that we're working on right now, as well as some other study resources that I've been doing. And thanks so much for joining the channel. Appreciate you coming here. He says, which book are you referring to? Yeah, so this is the Data Structures and Algorithms in Python book. This is I believe, a collegiate level course for teaching DSA in Python, and just using Python as its, course or programming language of choice for teaching these information. But yeah, I have a PDF copy provided in the Discord for all those members as well, or you could just look it up online if that's something that you're interested in as well. Okay. Roth says, keep going, we'll check back on you. Awesome. Thanks so much for stopping in, Roth. I'll see you later. Alex White says, I just got the M4 Pro, which I came from Intel Core i5 MacBook Pro. Yeah, I had the 2016 MacBook Pro, and I bought that and I sold it about 2 days. I took it back. I returned it about 2 days later and then I tried again with Mac about 2 years later and bought the 2019 MacBook Pro, or 3 years later, bought the 2019 MacBook Pro, and I returned that one as well because those Intel chips were so bad for those Macs. They were just so slow, and I was just like, I'm not spending this amount of money for this little of performance and this it just was not. It just was loud, hot, slow. But then this M3 chip has been the fastest chip I've ever experienced. Gus, thanks so much for joining. He says, hi, sorry, I think you meant a to the power of log a to the x is equal to x. Um, I guess that could work, but this is just represents b as in base for log base. That's kind of how I do it. So the variables could really mean anything for whoever the context of whoever user or whatever, right? Anthony says, I have an M2 Pro and I have no desire to upgrade. Yeah, exactly. So if you get that M2 Pro, honestly, it's probably the best bang for your buck right now is getting that M2 Pro, MacBook Pro. Rohit says, I suggest a Mac Mini, which has very good specs at a good price. Yeah, the Mac Mini I heard about that also. They're like $500 and they're got the M4 Pro chip in there and they've got good RAM and storage and stuff. So the only thing is just you can take it around, but you just also have to have either a TV or a monitor to plug that in. But it is extremely portable because it's so small. But the laptop gives you that portable screen aspect. Muna says, I think I'll get a Mac M3 Pro. The specs I want seem to be for about $1,600 on Best Buy, so it'll probably work over the summer to pay for it. Yeah, maybe also check out the M2 Pro, and you might be able to save yourself maybe 300, 400, $500 on that one. And honestly, it's literally like milliseconds of difference in speed between the M3 and the M2. They don't even upgrade like the megapixels in the camera, really, I don't think, until the M3 to M4. So that was the only consideration I was going to have to upgrade because I stream and I wanted a better camera for my computer. I was thinking, okay, well, if they add a 4K resolution camera to the M4, I might upgrade and get some value out of my current one. Yeah, it's barely new, but if they got a new camera, I would definitely do it, I think. But they only increased it like 12 megapixels, so no upgrade for me. um, I have the 14-inch MacBook Pro, the M3 Pro MacBook Pro. Is there a way to show? I don't know. Legend says compatibility would depend on distro to choose. You choose to use. You may encounter some applications that may not work, but most of the CS related applications, such as Docker, will be okay. Alex White says only upgrade to a high M series chip if you're coming from Intel chip. Pardon me. Pardon me, guys. Been talking for like 4.5 hours straight, so please bear with me. All right. Coming from the Intel chips, it's not worth upgrading from M chip to M chip. Not yet, at least. Yeah, exactly. Maybe if you were wanting to go M1 to M4, you could make that leap if you had the funds to do so. But even then, it's probably not even super worth it at this point in time. Okay, so let's continue here. So we're on 3.8. So we're trying to order these functions in terms of their asymptotic growth rate. So we know that looking at this first row, we know that the 2 to the power of 10 does not take in any data inputs, and so it's going to be constant time. So that's going to be our fastest algorithm for this for large data sets. Next would be this is going to equate to 2 to the power of n, which would be exponential. So our rule was from our notes that if we have a number and we have a log being raised, right, the answer to this problem can be reduced down to just the number inside the log. So this will be just equal to f of n. This is the same thing as f of n is equal to n, which is linear, right? So this is a linear function based on our log rules. And so this would come next in our problem. So the 2 to the power of log n would come next. Right, perfect. And so lastly, the 4n log n would come next. Right here, as you see by this graph. Now I'll go ahead and add on the 2 to the power of 10 so you can see. Right. So, right, that's a constant function. So for no matter the large input, we're always going to get back that value of 1024, whereas the blue function will come next, and then the red function will come next. All right, moving on to the next one. We have Let's catch up with the chat here real quick. I appreciate you guys joining me. Thank you. My name is Michael. For those who are new here, I am a 25-year-old self-taught computer programmer. I have a background in, I have a bachelor's of science in human biology. I graduated back in 2021 from a state school here in the United States. I have a minor in chemistry, and I specialize in the chemical aspect of, human biological um, molecules and things along those lines, functions, physiology, things like that. Um, Physiology. And I work currently at a biotech company as a formulation chemist where I make biological controls used in vitro testing for uh, clinical diagnostics. Meaning, I know that's a lot of words, but meaning like in a lab setting, physicians and other types of doctors would run patient samples against my control samples to determine and make confident decisions in their diagnostics for certain diseases and patient ailments. And, so I make these biological controls in a large scale, and then these products get, bottled into small vials and sold into those circumstances. So that's kind of a background on my job. I work in a lab. I do a lot of math, working with chemicals and concentration solutions, matrices, chemical matrices, balancing and figuring out, predicting the effective concentrations of bulk solutions. So that's kind of my current job right now, and I thought it would be very interesting to incorporate computer programming into that. And so that's what started me down this rabbit hole into CS50P. I started at the end of June, or the beginning of June, in CS50P, and completed that course very part-time throughout the summer of 2024. I submitted my final project of August of 2024. And then in September of 24, just a few months back, I really started getting serious and started developing a passion for learning and creating more projects. It just sparked from there. And I created this channel, and I've been documenting my progress kind of like as a video journal series and a way for other beginners to have an acquaintance, network with someone in a similar situation as them, learn these concepts as well. Maybe you're a student, maybe you're a professional, maybe you're just someone that's wanting to develop a new skill like I am, you know. And I welcome all those types of people. I have a Discord link below where I compile all my study resources into one location. So if you're interested in seeing that, feel free to join the Discord there below. And yeah, that's just that spiel for now. So let's go ahead and look at the next set here. So we have, let's first evaluate the time complexity of this first function. So we have a 3n, which is going to have an O of n time, right? Linear time. And we have 100 log n, which is going to be logarithmic time. So this is going to have an overall time complexity in O of log n time. No, O of n time. The linear time is going to bottleneck this function and create an upper bound or upper limit in linear time because it is the slowest function in this this grouping. This function is also in linear time, but it has a smaller constant associated with it, or a larger constant than this one, so we'll have to keep that in mind as well. Whereas this one is in exponential time, and so this one is going to be our last one, I'm assuming, just from our rules that we have. So let's go ahead, and I'm gonna first just go ahead and create some space holders. I'm gonna put that 2 to the power of n at the end of our list, because I already know I'm already assuming that that one is going to be the least efficient. So we have a 2 to the power of n function, which takes that exponential form, right? We then have another function here for, I want to look at 3n plus 100. Well, I actually want to first look at 100 log base 2 of n. So this function creates a very vertical slope, extremely vertical slope. This function is not efficient at all. Oh, so we also, Yeah, log base 2n. So this function is extremely inefficient for large data inputs. Now if we go ahead and add a 4n out front here, or a 3n I mean, that just slightly skews it ever so slightly to the right, like a little bit of positive slope um, uh, into the right? So that barely impacted that at all. So just based on that note, I know that that 4n function here is going to have more efficiency for larger values. Now, as you can see, we have a little bit of a gray area found within these functions where up until the data point of x equals 4, we don't transition until the linear function takes precedent. So this one would be ordered as the fastest would be the 4n function. The second fastest would be the exponential function, which is interesting, and then the last one would be the 100 log, the 3n 100 log n. Right? That one would be the last function. Okay, so let's look at the next one here. We have n squared plus 10n. We have n cubed, and we have n log n. Okay, so we know we have a cubed function, we have an n log n function, so we know that the n log n function is going to be more efficient than the n cubed function, so we can go ahead and say that right off the bat. So let's go ahead and put some placeholders here, and let's say that the n log n is going to go here, and the n log n function is going to go here, whereas the n cubed function is going to go here. Now we need to determine if a quadratic function, right? We have a quadratic function being added with a linear function. Now, we know that the quadratic function is going to kind of override this for big O's notation's sake, and this overall function is going to have a time of O of n squared, right? Which would, in theory, according to our notes, we have quadratic, then cubic functions, then exponential functions. So the quadratic would come before the cubic, which would come after the n log n. So let's go here and put the quadratic function here. Okay, like that. So let's go ahead and check our answers with Desmos here. So we have n to the power of 2 plus 10n. We have n cubed, and then we have n log n, right? So we predicted that the interesting. Oh, I'm dumb. I have this in the wrong. I put this in the wrong spot. The n log n is supposed to come forward, like that. So we predicted that the n log n was the fastest, the quadratic was the second fastest, and the cubic function was the third fastest. And as we can see, oh, interesting. We have some interesting behavior going on here. So our n log n function is by far the most efficient function here, right? Right. Now, the blue function has efficiency precedent over the red function up until this x value of 3.7. So this is fairly small, right? So actually, the So the 10N here skews this. Yeah, so it's interesting, if we were to get rid of the 10N here, the 10N makes this um, behavior interesting. It really brings this red line in tight, and you don't get that efficiency crossover until up here. But you still, for larger inputs, you still would prefer the red, even though they're both terrible. All right, let's get caught up on the chat here. All right. Muna says, I currently have a cheap Windows laptop that I've been using for a few years. I've never used a Mac before, but the M2 does seem more appealing. It's $300 cheaper than the M3. It's one of the most popular ones, and it's actually really nice to use. My college have them in the computer labs, and I find them really easy to use. I normally use Windows. If it's only $300, I know $300 in the grand scheme of things. If it's only $300, I would go for the upgrade to the M3. To be honest, if it's really only 300, if it's anything less than like 350 to do the upgrade to M3 versus M2, I'd probably just go for the M3 and get yourself maybe 2 more years of use out of it. Alex White says, using Mac will definitely be a learning curve, but I feel it's a lot more straightforward. And as Michael was saying, it really limits you compared to what Windows OS allows you to do. Alex White says, I would get the M3 if you get the funds because the core difference is where it may be worth, in my opinion. But if M2 is still really good, yeah, I would do the M3 as well. If it's only $300, if it starts getting past 400, then it's probably not worth the upgrade. But 300, I think that's in the right ballpark to do it. I would do research comparing the two Mac, and just understand the chipsets will definitely help you make the decision. I also think they have different screen qualities, but I'm not really sure. Muna says, maybe I'll get a test drive. I currently have a ThinkPad, which I heard goes well with Linux. I'll have to research how to download it without messing up Windows. He says, it will probably come down to cost for me. I'm researching prices on Best Buy, and it seems I can get the 14-inch M3 Pro for $100 cheaper than the 15-inch M2 Air. Just came back from work. Avinash, I appreciate you coming in after work. Thanks so much for joining me. He says, I just came back from work. The goal is to get a solid 3 or 4 hours of studying. Grind never stops. Yes, we've been going for almost 5 hours this stream, so I'm right there with you. Luna says, is your laptop connected to a monitor, by the way? Yeah, I do have my laptop connected to a Dell curved 27-inch 160 hertz refresh rate monitor. It's one of those old ones. It's not an old one. It's a fairly new one, maybe 2.5 years old. I used this mainly for gaming back in the day, but like I said, I don't game anymore. I sold my gaming setup. I do like to play Nintendo Switch, though. I do play Animal Crossing and Smash Bros. And Mario and all that stuff. I do like Nintendo games. I was a big DS Game Boy player back in the day. Pokemon, huge Pokemon player back in the day. I grinded my Blastoise all the way to like level 97 by like no rare candies, just pure grind and XP in the Victory Road back in Fire Red. I loved that game. I played it so much. But yeah, and then so I like to play Animal Crossing right now, Zelda. Those are the only kind of games. But every once in a while, I would much rather spend my time learning to program and teaching myself skills. I've kind of just phased out of that point in my life, unfortunately. But I connect it to my monitor. I don't connect it directly. I connect it into this Dell dock. Um, it's like the WD0019 or something like that. Now, I will say don't get this dock if you're going to use the Mac, because this is made specifically for Dell and Windows stuff. It does connect a single monitor to Mac using the display port, but the HDMIs do not work for double monitor. I would have to use a USB-C, and I don't have a monitor that has a USB-C. But Eventually, maybe I'll do a double monitor. I'll have to get a new dock or something. But Avinash says, stop gaming too. Maybe I'm just getting older, but I'd rather just be productive now. Yeah, exactly. Now, no knock on anybody that does game. I think gaming can be a great way to de-stress after a long day of doing work. But I often found myself slipping into a slope where I was just spending way too much time actually playing games. And I would go through these cycles just kind of feeling guilty, beating myself up. And then also, stop it, kitty, stop scratching the wall. I was I was just finding that I would get angrier, like if you get competitive in games and it affects your mood a lot. And I just didn't like the kind of person that was the games were making me become with heavy use. And so I decided to step away and break that habit. And ever since my senior year of college, I've kind of stopped playing games, and I'll maybe pick it up. I'll get in and play a game of League of Legends every twice a year or something like that. Minecraft maybe, but I'll play my Switch if I want to play something in the free time. Especially since I'm unemployed college graduate. That would give you some motivation to hop off the games and do some grinding, right? Well, underemployed. Gotcha. That's funny. Okay, so that was 3-8. We ordered those. Okay, let's go to 3-9 key dot pi. Oh, we need a R in there. Let me check my phone real quick. Make sure I don't got any. Okay, we're good. We are good. Okay, so 3-9. Show that if d of n is show that if function d of n is O of f of n time, then a times d of n is O of f of n for any constant a is greater than 0. So if d of n is O of f of n time, we know that, similar to the problem from before, that d of n is equal to, right, so this is d of n is O of f of n. It's like this, right? My kitty is giving me growls. She's hungry. They want food. I'll have to feed him in a sec. I'm gonna wrap it up here. We're almost at 5-hour mark, so. All right. Show that if d of n is O of f of n, then a d of n is O of f of n for any constant that a is greater than 0. Muna says, I've been watching you for an hour, but seeing you go deep into learning a new skill from interest kind of inspires me to learn something. I think I'm going to go through a calc textbook to deepen my math skills before college. Yeah, that's a great way. It always definitely would help and give you an edge to come into college. I think a lot of college kids go into college expecting to just learn everything right then and there and walk away being experts in the material. Now, some kids get there and they realize that's not the case, so they start grinding away while they get there, like in the library and things like that. But honestly, my advice would be is if you have the ability to come into college with some already experience in those classes, maybe you have taken some stuff on study.com or Sophia or something like that, or just even watching Khan Academy videos and YouTube videos, um, it'll just give you so much more of an edge to participate in class, because rather than just sitting back in the back of the lecture hall, taking in the information, having it go one in, one at the other, as soon as you leave the class, you forget it all because it's the first time you've ever heard it, and you have 3 more classes that day that you have to go worry about. Yeah, so instead of that, you go into the class already having known the material. You can then create a discussion with your professor. When he asks questions, you will be the one to respond, and you will have a discussion. And by you being able to be one on one with your professor in this lecture hall of people, A, you will look impressive. B, you will further develop your knowledge because your professor is directly tailoring the lecture to you at that point. So I found that I did that with some of my classes, and it really helped to boost my learning, and just by participation, you get what you get out. So show that function d of n, if function d of n is in O of f of n time, then a times d is O of f of n time for any constant that a is greater than 0. So a times d of n, well, that would be, I mean, that would be true because essentially a times d of n is just like some constant times our d of n. A would just resemble some constant c in this case greater than 0, right? So um, right, so if we just plug this in and say, for this problem, if d of n is in O of f of n time, then by then the a d of n by a is essentially the same as d of n by some constant c. C and a are doing the same thing. Okay. You're correct in the essence of your reasoning, but let's formalize the mathematically to ensure precision. Definitions and key idea. If d of n is in O of f of n, then by definition, some obscure bullcrap. Okay. Please reduce the jargon and make it simple. So big O notation tells us how fast a function grows, but it does not care about multiplying by constant. It only cares about the general shape of growth as n gets really big. If d of n is O of f of n, it means that d of n grows no faster than some constant multiple of f of n. For example, if f of n is n squared, then d of n could be something like 5n squared, and it's still O of n squared. Okay, so d of n is O of f of n, which means that the function d of n just resembles whatever f of n's time, is. Okay. Now, if you multiply d of n by another constant, a is greater than or equal to 0, you're just changing that constant multiple. For instance, d of n is equal to 5n squared. Multiplying a2 gives you 10 times n squared. This doesn't change the fact that both are still growing like n squared. So multiplying by a doesn't change how fast d of n grows compared to f of n. That's why a times d of n is still O of f of n. Right? So this will say, let me copy this guy and see if it likes this response. Yes, that inequality is the key to understanding this. Let's break this down step by step. So if d of n is in O as a part of O of f of n, meaning that d of n is less than or equal to some constant c times f of n for some constant c is greater than or equal to 0. Greater than 0. So multiply both sides by a, gives you a times d of n times a times c, which is c prime, right? So if we multiply both sides by some a value, a times d of n is less than or equal to c times f of n, right? But we need to multiply both sides by a. So a times c times f of n. Well, this just becomes a times d of n still, right? Is less than or equal to ac times f of n, right? So, and we'll say if d of n is represented by uh, a similar time complexity. If d of n is represented as having a similar time complexity to that of f of n, right? Multiplying a on both to d of n only impacts the constant c value. This would slightly skew our graph / function but remain with an overall time complexity of O of f of n. Right. So basically all this said was if d of n is resembles the time complexity, right, of O of f of n, whatever f of n is, right? So if f of n is a linear function, then so is d of n in some form. If f of n is a quadratic function for a big O notation complexity, then so is d of n. So if that's the case, if we just multiply some value a by d of n, that's essentially just saying we do that here. We just multiply a by both sides of our big O notation formula. Now, this a only impacts with like terms, which would be some constant value c, and so this would combine for some total value ac. Meaning that the graph D would only just be skewed slightly by some more constant A, but remain and keep the overall time complexity originally, right, of f of n, O of f of n, if that makes any sense. Cool. Hopefully that made sense to you guys. Let me know how you felt about that. Okay, let's do one more problem here, and then I might go ahead and call it for today. We've been streaming for 5 hours and 10 minutes now, so a long, very, very productive stream here, working on these problems. Continuing, I think we went back and did refreshers on big O notation, big omega. We really solidified in our chapter 3 notes here some examples of big O and big theta notation and how I wasn't originally thinking about these in applying them to an algorithm by algorithm basis, right? I was thinking that these were rules that were followed via some sort of underlining placement on the graph itself, whereas if you have your function here, it's bound by this, it's bound by that on the top and bottom, those must be big O and big omega. But no, the function itself, right? So for instance, if we have some function f of n where you're trying to find a value in an unsorted list of values n, right? So if we have a list of values unsorted, so it's like 1, 5, 2, 7, it's unsorted, and we want to find a value, so we say like we want to find 3 in this set, and if it's random. So the worst case scenario is that we have to loop through and search every number in that set, That would be an O of n time, right? We are searching and comparing each number to our value, desired value. The best case scenario for omega of n time, right? That would be O of n time for the worst case. The best case scenario for this specific algorithm example, basis by basis, right, would be that what if the algorithm finds, or the function finds, that the value is in the first place, meaning that it didn't have to loop through any more values, it just found it right off the bat and returned it. That would have a time complexity of O of 1 time. So the function in a best case scenario would have an omega time of a time complexity of omega, big omega of 1 time, or constant time, right? Now, theta, that's a different story. We've got to get into that one. I, I am not the best at that one yet. We will hopefully hone that one down tomorrow. Okay. We need to rename this guy and add an R out front. Cool. Eclipse says, I'm too dumb to understand what you're saying. No, don't say that, man. I promise you, I felt the exact same way literally 3 days ago. 3 days ago, I felt the exact same way. I had no idea what any of this meant. I had no idea what it means, how to work it, how to solve it. But today, 3 days later, little by little, hour by hour, problem by problem, we've accumulated some knowledge, and we now are able to kind of, solve some notation, to solve some time complexity notation problems, right? So don't put yourself down because you don't know it right now. You might just not know it right now because you haven't actually tried. So give yourself some benefit of the doubt, my man. Don't hate on yourself. Okay, so 310. 310 says, whoops, got some fuzz on my finger. Show that if d of n is O of f of n time and e of n is O of g of n time, then the product d of n times e of n is O of f of g of n time. Okay. Okay, so if d of n, right, if d of n is less than or equal to some constant c times f of n, right? And we have some value of g of n, e of n, I'm sorry, is less than or equal to some constant c times g of n. We want to prove that c, that right, d of n times e of n is equal to c squared times f of n times g of n, right? All right, Jimmy Jim says, is O like operation time or something different? It uses a different constant. O is so big O notation, Jimmy G, like we've explained it in the past. So big O notation is the worst case scenario that the algorithm or the function will run, meaning that it is bound on the worst case scenario or by the bottlenecking function found within the polynomial or whatever it is. So that's what big O notation refers to as the the function with the slowest growth rate found in the algorithm is kind of the interpretation, or I'm sorry, the function with the fastest growth rate, meaning that it grows fastest, thus meaning less inputs can be managed in more time. Muna says, do you recommend any resources to learn the math needed to get into data structures and algorithms? To be honest, besides just basic algebra and arithmetic, um, it's I I would just say like functions really. Functions are so if you took pre-calculus, that's where you get introduced into functions and things like that. Um, and like so pre-calculus is huge. I think is probably big. Um, I don't think derivatives are super useful for right now. We haven't used anything with knowing needing to know that, and so probably just basic pre-calculus concepts in algebra. We had a recommendation to use C2 for this one. So we'll do C times C2 like that. Okay. So then we need to prove that the product is O of f of g of n. F of n, g of n. Hey, stop. Yeah, so the product, so this overall time complexity now is going to have a time complexity of O times f of n times g of n. Just based off this, right? Right? This function, right? We've broken this down now to say that, okay, this is our function, right, that we're solving for, d of n times e of n. We want to see what time complexity this is. Well, we're going to drop off the constants, and we know that f of n is an O of n time. We know g of n is an O of n time, so we are an O of f of n times O of n times g f. Oh my god, that was such a bad stutter. O of f of n times g of n time complexity. This is a tongue twisters galore out here. Oh my gosh. Struggling. Okay, let's throw this into the almighty orb and see what he has to say. All right. To show that d of n is O of f of n and e of n is O of g of n, and their products d of n times e of n is O of f of g of n times g of n, let's formalize this proof. Break, use simple terms, less math. So d of n grows no faster than some multiple of f of n. Think of that as, right, got you. E of n grows no faster than some multiple of g of n. So e of n is less than a big version of g of n. Got you. What happens when you multiply them? If you multiply the two things together, you get d of n times e of n equals less than big version of O f of n times big version of g of n. Stop, Sky. My dog's chasing the cat around. Stop it. Stop it. Leave her alone. So conclusion, grows no faster, e of n is an O of f of g of n time. So we'll say here, we'll like drop the constants. Cool. That's the answer to that one. All right, Muna says, for some reason I thought it would involve higher math like calculus. I have math background, but I need to learn Python better. Yeah, for so far from what I've been seeing, at least up to chapter 3 through chapter 3 right now, is I haven't used any math other than basic algebra and, some statistical symbols. What I mean by that is you'll see um, you'll see like the is in form, the like what is in Chappy GPT here. You'll see this symbol and stuff like that. These are mathematics symbols or math symbols that you find in like proofs and discrete mathematics and statistics and things like that. Yeah. Hey Nani, I appreciate you coming in and joining the chat and leaving a message. Thank you so much. I hope you're doing great this weekend. Happy Saturday to you. Okay, we completed 10 problems here, you guys. I'm gonna go ahead and let's get add all here, and let's go ahead and commit this. Chapter completed. Some chapter 3. Cool. So now we can push that to the repo online. So yeah, if you want access to these notes that I've been making and all of these solutions up through chapter 3 so far to these problems found at the end of the chapters in data structures and algorithms in Python, you can go ahead and check the um, description below and get access to for my GitHub and get access to this repo. All right. All right, you guys, I am pretty gassed. I've been talking to myself and to you guys for over almost 5.5 hours now. Wow. Boy. Let's go ahead and check on the channel and see what we're looking like so far. We've had a very long, successful stream. Let's see how much we've grown today so far. Oh boy, we're at 291 subs. We are nine subs away from 300. Oh, super exciting, super exciting. Jimmy Jim says element of E. What do you mean element of E, my friend? Jeremy says discrete mathematics is really useful if you're going to pick up an area to study. Yeah, discrete mathematics. To be honest, I started the MIT 6.042J course, which is the computer mathematics for computer science class, and it was really difficult. Let me tell you, I completed and I posted the study along and watch along to the first lecture on this channel actually. So it's currently up on my channel, but I started to watch the second lecture and oh my god, they just got in so fast and no one asked any questions in the lecture the whole time, and which is just impossible. I get these people are really smart, but how do you not one person has the cojones to ask a single question? Like you guys are paying thousands of dollars for this experience and you're just gonna let these concepts go right over your head and not ask a single question in lecture? I just didn't get it. It was like so mind-blowing that apparently everybody in this class understood what this guy was saying when he was speaking at like light speed. So it took me about it took me about an hour to get through the first 15 minutes. So I have since not gone back, let's say. All right, you guys. That is going to do it for the DSA portion of today. Ooh, I need to put all of these guys in the chapter 3. Whoops, these were in the chapter 3 actually. We need a new folder, chapter 3 keys. We'll put this into chapter 3. We're going to throw all of these into here. Except for the notes. There we go. Now that has proper formatting. So we will go ahead and let's git add, git commit, fixed dir flow. All right. Jeremy says MIT students probably just know it already completely. That's what I was thinking. I was like, okay, it's either I'm really dumb and these kids are just beyond me, or this is just like, or no one's getting their money's worth in this college. No one's willing to ask any questions. All right. I appreciate you guys joining me here today. Thank you so much. And for those that are new and have subscribed today and joined the channel, thank you so much. I really appreciate you guys make this, you guys make this a lot more enjoyable, more motivation. I really appreciate all of the help you guys have provided. What's up with this formatting? I have to do this again. Git add. Okay. Cool. All right, so this is going to do it for today's on the data structures and the algorithms portion of today. We are going to jump back into these problems tomorrow, guys. So if you want to see more practice with DSA, we got, a good 20 more problems to go here. So feel free to follow along. Appreciate you guys joining me for today. I want to quickly, before I go, I want to just show the new viewers that in the back ends of my stream, I typically like to work on a personal project, but we've just been going for 5.5 hours now studying DSA and really solidifying these concepts. So I'm a little bit burnt out. Sorry, bear with me, guys. But maybe tonight, honestly, maybe if it's late, if I have some time later this evening after maybe my girlfriend goes to bed, or is doing something maybe around 9:30, 10, I might hop back on and stream for a little bit, do a late night session and work on some of the personal project. But I just wanted to show you, the new people here, what we're working on for the personal project. So I've already created on my channel a task tracker application. We built that from start to finish, all on the channel here, and we have that pushed to GitHub. So feel free to go check that out on the GitHub, star it if you would be so kind, and use it. But so this project that we're now working on utilizes a lot of the aspects that we've currently yes, I'm on West Coast time. So Muna, if you want, I always post my stream announcements in the Discord. So if you're in the Discord, I will post an announcement if I do go live later this evening for a double session, a daily double, we'll call it. But the odds are pretty slim that I'll come back on later tonight. I've already been going for 5.5 hours. So that's a lot of studying for one day, in my opinion. We don't want to burn out here. But so this project that we're working on utilizes object-oriented programming, and the whole idea of this is it's a small business manager application. Now, small business users will be able to essentially have features to add inventory, manage that inventory, and then create and generate sales from those inventories, and then develop reports based on that. So the goal is the user can load in items into their inventory via this item class. They can convert those items into for sale items, which have additional parameters associated with them. And they can further convert that item into a sold item, which have additional parameters relating to sold items, right? So we've set up these structure for how our objects are going to be oriented. But now we actually have this larger file here, upwards of 356 lines of code so far. Where we're actually running the script and where people are seeing things taking place. So I'll show you guys a quick example here of what's going on. So if I go ahead and actually just run this program, we get prompted with, would you like to open the Small Business Manager by Michael Deming? So we'll press 1 to enter, and we're in our system here. So we have the Small Business Manager 1.0 by Michael Deming, and we can press 1 to access the inventory. We'll press 1 and we're into the inventory manager section of our project, where we can add items, we can remove items, we can find and edit items, we can view inventory, and then we can go back to the main menu. Now, I don't have actually any functions set up at the moment that currently do any of these features, but we will be getting there. I promise. We'll work on some more of this tomorrow. I will definitely be working on this tomorrow. I will do my best to allot a hard cutoff for when we'll switch from DSA over to the personal project, because I do want to continue I do need to continue practicing with code, rather than just learning the back ends of it. I need to keep working and on my code, getting faster, getting better at being more Pythonic. Just putting in those sheer hours, physically typing out code is what's going to get you to be better at it. So I will be working on this tomorrow. I will gonna allot at least 2 hours tomorrow to work on this. So feel free tomorrow. We're gonna probably do about 2 and 2, 2 hours on DSA, 2 hours on this program, and yeah. So we have this system, and so we can if we press 1, we'll probably get an error here. So or we get add new item to inventory. So because we have the add item system here, I'm going to remove this guy here. Yeah, I need to go here, delete like that. Cool. So if let's clear out of this. Let's run this one more time. So that menu should be fixed now. Yeah, add inventory item, right? So it works pretty good here in terms of its overall like functions and processes. We've got like a good flow for how we're going to manage all these different menus and things along those lines, because when we're not working with a GUI or graphic user interface, we need to develop these kind of flow processes within our terminal here. So we have like the clear terminal function, which clears the terminal for our loops and things like that, and we have a create menu, which creates these menus using a list of options and a prompt provided. And so over the course of the past few weeks, we've been working on this and creating functions. So if you're new and wanting to actually get some hands-on experience and watch someone code a live, maybe beginner to intermediate project, this is definitely the place to be. So feel free to follow along to the channel and to the Discord, and we'll see you guys. We'll work on this and definitely as we keep going here. So tomorrow, I think what we're going to do is we're going to keep working on this inventory, run inventory, menu, and we're going to add in the run add item function. So we have this built so far, where we just ask the user for the name, the cost, size, number, and then date created. And so we have these other subsidiary functions right here that are categorized into our operational functions category. So we have like process functions, which are just like our menus and our flow, and then we have operational functions, which manipulate the flow and everything. So and the data associated. So we have a generate item number, where we try and find the current most item in the list, like the most recent item added to the inventory, and we detect that we get the item number from um, that data value, and then we add one to that item number to get the next item available to load in a new item into the list, right? And then except if we get an index error, meaning that the list is essentially empty, in that case we return one for that is the first item that is loaded into the system. We have a date created generation where we ask the user to use the current date today. So if they were to buy an item today and load it into the system today, they would say, yes, I want to use the current date. If not, they have the option and ability to press 2 here and use a custom date in this format. Now, I do need to actually implement this detection of the custom dating and things like that, maybe with either regular expression or with the time delta filterings through the date time module and stuff like that. But if you have any questions on the things I say, feel free to ask along. I would love to answer the questions for you guys and give you the like clarity you're looking for if I can. Obviously, I'm not providing advice because I myself am learning, but if I can provide some input about something I have learned in the past, or you learn something from my current learning, that is the goal of all of this in the end. But yeah, so if you guys are interested in this and eager to see more of this, so feel free to tune in tomorrow. We're going to, or maybe even later this evening, we might do a late night session to grind away at this and really zone in. So thank you so much for tuning in, guys. I'll see you tomorrow or later this evening, depending on how I'm feeling. We learned a lot in DSA. We completed 10 of the problems in the back of the book, or the chapter 3, and re-solidified a lot of those chapter 3 concepts. So making a lot of progress and feeling really good. Thank you so much, guys. See you tomorrow.